Space is still full of mysteries, even with all the progress science has made. The universe keeps surprising us with strange things, from strange signals beaming across the universe to planets that defy the laws of physics. What lurks in the dark corners of our universe? Could there be unknown forces shaping reality as we know it? And what secrets are hidden within the vast, uncharted reaches of space? For years, astronomers and space enthusiasts have been fascinated by a mysterious star known as Tabby's star, officially called KIS 8462852. This distant celestial body, located about 1,400 light-years away in the Cygnus constellation, has baffled scientists with its strange and unpredictable dimming patterns. Unlike most stars, which dim and brighten in predictable cycles, Tabby's star experiences sudden and irregular drops in brightness, sometimes by as much as 20%, without any clear explanation. Tabby's star, also known by its scientific designation KIC 8462852 in the Kepler Input Catalogue, is a mysterious star located in the constellation Cygnus, approximately 1,470 light-years, or about 450 parsecs, from Earth. This star system consists of two stars, an F-type main sequence star and a red dwarf companion. Its odd and unpredictable changes in brightness have baffled astronomers and sparked widespread curiosity, leading to various hypotheses about its nature. The strange dimming of Tabby's star was first noticed by citizen scientists working on the Planet Hunters project. They discovered that the star's brightness fluctuated in unusual ways, with some dips as large as 22%, a significant amount compared to most stars. These fluctuations were detected by data collected from the Kepler Space Telescope, which was originally designed to find exoplanets by observing slight changes in the brightness of stars. While many ideas have been proposed to explain these irregular changes, none of them fully account for all the mysterious patterns in the light curve of Tabby's star as of 2024. One hypothesis even suggested that the fluctuations could be caused by an alien megastructure orbiting the star. However, most evidence seems to rule out this idea. In September of 2019, astronomers proposed that the dimming of Tabby's star might have been caused by fragments from an exomoon, a moon that was once orbiting another planet but was disrupted, possibly due to a collision or some other catastrophic event. Interestingly, Tabby's star isn't the only one with large and irregular dimming events. Other stars, known as young stellar objects, YSOs, also experience dimming, but their patterns are different from those seen in Tabby's star. The star's most common name, Tabby's star, comes from American astronomer Tabitha S. Boyajian, who was the lead author of the paper that first reported the irregular light fluctuations back in 2015. It is also known as Boyajian's star in her honor. The nickname WTF star is a reference to the subtitle of the paper, Where's the Flux?, which drew attention to the strange drops in the star's radiative flux. Another playful nickname for the star is LGM2, which references a famous historical event in astronomy. The first pulsar discovered was once thought to be a signal from an extraterrestrial civilization and was called LGM1, Little Green Men. Similarly, Tabby's star's strange dimming events made some wonder if they could be a sign of something out of this world. Additionally, Tabby's star is also listed in various astronomical catalogues, with different designations depending on the catalogue. For instance, in the Kepler Input Catalogue, it's listed as KIC 8462852, and in the Tycho II catalogue, it's referred to as TIC 316266651. Tabby's star resides in the constellation Cygnus, which is located in the northern part of the sky. It lies about halfway between two bright stars, Deneb and Delta Cygni, forming part of the Northern Cross. While Tabby's star is only a few arc-minutes away from the star cluster NGC 6866, it is not related to this cluster and is much closer to our Sun than it is to the cluster itself. With an apparent magnitude of 11.7, Tabby's star is not bright enough to be seen with the naked eye, but it can be observed with a telescope that has an aperture of at least 5 inches, about 130 millimeters, provided the sky is dark and free from light pollution. The star itself has been observed for over a century, with its first recorded observation dating back to the year 1890. Since then, it has been catalogued in several important astronomical databases, including the Tycho, 2-micron All-Sky Survey, 2MASS, and WISE catalogues, which were published in the late 20th and early 21st centuries. Most of the data on the star's fluctuations in brightness has come from the Kepler Space Telescope, which monitored over 100,000 stars from 2009 to 2013. Kepler was designed to study stars and exoplanets by observing the light curves, the changes in brightness, of distant stars. This was a part of its mission to search for planets outside our solar system. In May of 2017, Boyajian and her team reported another significant dimming event, which they named ELSI. This event, which possibly started in mid-May of that year, was detected by the Las Cumbres Observatory Global Telescope Network, particularly by its telescope in Maui, Hawaii. The event was observed and verified by other observatories, including the Fairborn Observatory in Arizona and the LCO Canary Islands. Several other telescopes around the world joined in to gather data on the event, as these dimming events are often short and last only a few days or weeks. The astronomical community went into a frenzy, with astronomers dropping other projects to focus on this rare opportunity. The event showed a complex pattern, similar to another observed dip that occurred at about 759 days into the Kepler mission. Later, in June of 2017, another dimming event named Celeste was detected. This one was first noticed by amateur astronomer Bruce L. Gary, and while there were some fluctuations in brightness over a few days, the dimming continued to increase over time. Boyajian and her team continued to monitor the event, noting that it was approaching a 2% decrease in brightness. This event was further studied by astronomers, and more observations were made, including some from the famous twin Keck telescopes. A third dimming event, known as Skara Brae, occurred in August of 2017. This event saw a dimming of about 1% and lasted for a few weeks before the brightness of the star recovered. Tabby's star has been the focus of intense curiosity among astronomers due to its unusual and unpredictable behavior. The star has experienced multiple dimming events, some of which are so deep and irregular that they challenge our understanding of stellar phenomena. These dimming events are not caused by typical astronomical objects like planets, but instead seem to involve something much more complex and mysterious. The first significant event we'll look at occurred on 5 September 2017, when a major dimming started. This event, named Angkor, marked the beginning of what would become one of the most significant dips in brightness observed that year. As of 16 September 2017, the star's brightness had dropped by between 2.3% and 3%, making it the deepest dip recorded for that year. This marked a new chapter in the mystery of Tabby's star, which had already been puzzling astronomers for several years. This event was followed by another smaller dip around 21 September 2017. This particular dimming was only 0.3% deep, but it was brief, and the star completely recovered its brightness by 4 October 2017. However, what really intrigued astronomers was a brightening event that started on 10 October 2017. For about 2 weeks, the star's light increased, which was a stark contrast to the usual pattern of dimming. Bruce L. Gary, an observer at the Hereford, Arizona Observatory, and Tabitha S. Boyajian, the star's namesake, proposed a possible explanation for these fluctuations. They speculated that a brown dwarf, essentially a failed star, might be transiting near Tabby's star, causing the strange light curves. This hypothetical brown dwarf would have an eccentric orbit, taking about 1,600 days to complete one full orbit around the star, which could explain the periodic brightening and dimming. By November 2017, a fifth major dimming event began, reaching a depth of 0.44% by about 20 November. Over time, this dip deepened, and by 16 December 2017, it reached a depth of 1.25%. But just like the others, this dip started to recover as well. These fluctuations in brightness were constantly being monitored, and updates were released frequently to keep track of the star's behavior. As the year ended, Tabby's star was too close to the sun to be observed, as it was in a position where the sun's light made it impossible to see. However, astronomers resumed their observations in late February 2018. By mid-March, a new series of dips began. By 18 March 2018, the star had dimmed by more than 1% in a specific light filter, the G band, and about 5% in another, the R band, making it the deepest dip observed since the Kepler mission started its observations in 2013. 2 days later, on 24 March 2018, an even deeper dip began, with a brightness loss greater than 5%. This dip was confirmed by a volunteer observer named John Hall. By 27 March 2018, the second dip was starting to recover, but it was clear that something extraordinary was happening with this star. In 2019, the observing season began in mid-March, and the star reappeared after its annual conjunction with the Sun. Around this time, the Transiting Exoplanet Survey satellite, TESS, began to observe the star, capturing its light every 2 minutes between 18 July and 11 September 2019. During this period, TESS observed a 1.4% dip in brightness between 3 and 4 September 2019. The star continued to fluctuate in brightness, with at least 7 separate dips observed between October and December 2019. The deepest of these dips reached a depth of 2%. By the start of 2020, the star had recovered its brightness once again. Overall, the combined depth of these dips in 2019 was around 11%, which was comparable to the dips seen in 2011 and 2013. But this time, the dips were spread over a much longer period. What makes Tabby's star so fascinating is the unpredictability of its dimming events. Observations made by the Kepler Space Telescope show that the star experiences small, frequent dips in brightness. But the star also has large, irregular dips that occur without any clear pattern. The changes in brightness are far more significant than what would be expected from a planet passing in front of the star. In fact, even a planet as large as Jupiter would only block about 1% of the star's light, so the dimming events of Tabby's star must involve something much larger, possibly objects that could cover half the width of the star. The fact that these dimming events do not follow any predictable pattern further adds to the mystery. The first major dip, on 5 March 2011, reduced the star's brightness by up to 15%. The next major dip, 2 years later on 28 February 2013, was even deeper, at up to 22%. Another smaller dip occurred shortly after in 2013, reducing the brightness by about 8%. These dips are far greater than what would be caused by a planet, and they remain unexplained. There was even a predicted dip in February 2015, but due to a malfunction in Kepler's equipment, it was not recorded. Some long-term studies have examined the star's brightness over the past century. One study found that the star had gradually dimmed by about 20% over a period of 100 years, which is highly unusual for a star of its type. However, determining the accuracy of this claim is challenging because it relies on older photographic records, which require adjustments for changes in equipment over time. Another study, using the same data, suggested that the dimming might not have been real, but could have been a result of errors in the data. A third study, using 4 years of data from the Kepler Space Telescope, found that the star had dimmed by about 0.34% per year, followed by a rapid 2.5% dimming over the course of just 200 days in 2017. This rapid dimming was unprecedented, and it returned to its previous slow fade rate after that. In 2018, a potential pattern of dimming was observed, with a periodicity of 1,574 days, or about 4.31 years. This suggested that there might be some recurring cause of the dimming events, but whether this is a real periodicity or just a coincidence is still under investigation. In 2021, astronomers confirmed the presence of a red dwarf star moving along with Tabby's star. This small companion star is located about 880 astronomical units, AU, away from Tabby's star. To give you a sense of how far that is, it's roughly 180 times the distance between Jupiter and our Sun, or about 30 times the distance from Neptune to the Sun. To put it in even more familiar terms, it's about 5 times the distance to the Voyager 1 spacecraft, which, as of January 2025, is the farthest human-made object from Earth. For many years, scientists couldn't fully explain the strange behavior of Tabby's star, especially its mysterious dimming. Initially, It was thought that these variations in brightness couldn't be explained by normal stellar behavior, considering the star's type and spectrum. This led to the suggestion that something external might be blocking the star's light. A few different theories were proposed, but none could perfectly match the data scientists had collected. Some of these theories included ideas like interstellar dust, enormous planets surrounded by massive rings, a recently captured asteroid field, and even a theory suggesting that the star's system could be going through a phase similar to the late heavy bombardment, a chaotic period in the early solar system. There was even a bold hypothesis suggesting that an artificial megastructure, perhaps built by aliens, might be responsible for the dimming of the star. In 2017, however, a major shift in thinking came from astronomer Brad Kohler and others, who suggested that the dimming wasn't due to anything outside of the star itself. Instead, they proposed that heat, which would normally escape from the star, might be trapped inside, affecting how the star's brightness changed. This was just one of many theories being considered at the time, but it pointed to some internal processes in the star that might account for the observed dimming. Then, in 2019, a new theory emerged. Astronomers proposed that the dimming of Tabby's star could be due to debris from the destruction of an exomoon, a moon of a planet that was once orbiting another star. They suggested that fragments from this disrupted moon might be blocking the star's light. This idea was still in the early stages, and more research was needed to determine whether it could explain the observed behavior. In the same year, another group of researchers studied Tabby's star using data from several different space observatories, including NASA's Swift Gamma-Ray Burst mission and the Spitzer Space Telescope. They found that tiny dust particles, originating from material around the star, could be responsible for dimming the light in the way that had been observed. In fact, by October 2017, NASA concluded that the star's odd behavior was due to an uneven ring of dust orbiting around it. This explanation seemed to fit both long-term and short-term dimming events observed by amateur astronomers, such as Bruce L. Gary and the Tabby team, coordinated by astronomer Tabitha S. Boyajian. The mystery didn't stop there, though. Researchers started exploring the possibility that the dimming events might be caused by an object in a highly elliptical orbit, like a brown dwarf star passing in front of Tabby's star. This could explain the periodic changes in brightness. This hypothesis added another layer of complexity to the already intriguing puzzle. Scientists continued to monitor Tabby's star, regularly updating light curves, which show how the star's brightness changes over time. Interestingly, similar fluctuations in brightness were observed in other stars like a white dwarf that also shows unusual light curve patterns. These fluctuations were attributed to dust debris orbiting the star, providing further clues that the dimming might be due to material around the star rather than something within it. One of the most interesting explanations for the dimming of Tabby's star involves a cloud of disintegrating comets, which might be orbiting the star in an elliptical pattern, similar to the Oort cloud around our own sun. According to this theory, the gravity of a nearby star could have disturbed this cloud, causing comets to fall inward toward Tabby's star, blocking its light as they passed by. However, this theory raises some questions, particularly about whether there are enough comets to block such a significant portion of the star's light, since it was observed that about 22% of the star's light was blocked during dimming events. Further research was conducted using sub-millimeter wavelength observations, which are sensitive to cold dust in the outer reaches of planetary systems, like the Kuiper Belt in our own solar system. These observations suggested that a catastrophic planetary disruption, which could have caused comets and other debris to scatter into the star's inner system, was unlikely. Still, the idea of a disrupted asteroid belt remains on the table, and scientists continue to investigate the possibility. Some astronomers, like Jason T. Wright, proposed that if Tabby's star is younger than it seems based on its position and speed, it might still have material forming around it. This could include coalescing dust and gas, although studies from the NASA Infrared Telescope Facility and other observatories have found no evidence for this. High-resolution imaging and spectroscopy have also ruled out the possibility of large-scale planetary collisions, which would create enough warm dust to glow in infrared wavelengths. This absence of glowing dust suggests that, despite the occasional dimming, no massive planetary collisions are taking place. The idea of planetary debris causing the dimming also seems unlikely, given the rarity of such large collisions and the low probability that we would witness one during the Kepler mission's observations. In December 2016, another exciting hypothesis emerged. A team of researchers proposed that Tabby's star might have consumed an entire planet, which could explain both its temporary brightening, as the gravitational energy from the falling planet was released, and its subsequent dimming, as debris from the planet's destruction remained in orbit around the star. If this were true, the planet's destruction could have caused the star to briefly brighten about 10,000 years ago, and the current dimming might be the star returning to its normal state. In 2017, researchers Suzukiya and colleagues proposed an interesting theory about Tabby's star. They suggested that a massive planet with oscillating rings could explain the unusual dimming patterns that the star experiences. This idea was one of several attempts to make sense of the strange behavior observed in the star's light curve, which has puzzled astronomers for years. Building on this, Ballesteros and his team, also in 2017, took this theory a step further. They speculated that a large planet with rings might be accompanied by a group of Trojan asteroids, which are objects that share the planet's orbit, located at a specific point called the L5 Lagrangian point. They even calculated an orbit for the planet and predicted that another dimming event could occur in early 2021, followed by another one in 2023. Their model estimated that the planet could have a radius 4.7 times larger than Jupiter's, which is quite big for a planet, unless it's a very young one. They also proposed that the planet might orbit a red dwarf star about half the size of the Sun. This type of star would be easy to detect in infrared light, which could provide valuable clues. However, existing radial velocity measurements, which are used to determine the planet's movement, weren't strong enough to fully confirm the model. New measurements could narrow down the possibilities, though. This model also offered an explanation for the dimming event in May of 2017. It suggested that the planet may have passed behind the star, causing a temporary drop in brightness. The model predicted a decrease of about 3% in the star's light, with a transit time of about 2 days. If this was indeed the cause of the May dimming, the model further estimated that the planet's orbit would take about 12 years and have a semi-major axis, a measure of the planet's average distance from its star, of about 5.9 astronomical units, AU, which is nearly 6 times the distance between Earth and the Sun. An interesting feature of Tabby's star is the observed reddening during the deep dimming events. Reddening refers to the way light from the star shifts toward the red end of the spectrum, often seen when light is scattered or absorbed by particles like dust. However, in this case, astronomers noted that the reddening didn't seem to be caused by dust obscuring the star. Instead, it appeared to be the result of cooling in the star's outer layers. The cooling could happen if the efficiency of heat transport within the star is reduced, perhaps due to changes in how the star moves heat around internally. This might be linked to the star's strong rotation, which causes differences in its rotational speed across various latitudes. Some scientists have suggested that Tabby's star could be near the transition between 2 different types of heat transport, radiative and convective. A fascinating idea that has gained some attention is that Tabby's star might be experiencing unusual behavior because it's a system on the brink of a phase transition, a sort of cosmic tipping point. This concept is based on avalanche statistics, a theory used to describe how complex systems behave as they approach a critical point. Such systems often show patterns that look like a mix between order and chaos. The fact that other magnetically active stars in the Kepler input catalogue show similar behavior adds some weight to this idea. Some scientists have even speculated that the star's strange behavior could be linked to magnetic activity. Another more speculative theory suggests that the dimming events could be caused by a megastructure built by an alien civilization, such as a Dyson swarm, a hypothetical structure designed to collect energy from a star. While this idea has captured the imagination of many, not everyone agrees with it. Stein Sigurdsson, a scientist studying the phenomenon, has argued that this theory is unlikely. He points out that it doesn't offer the most straightforward explanation, especially in light of other potential causes, and is at odds with Occam's razor, a principle that favors simpler explanations. Nevertheless, he agrees that it's a topic worth investigating because it can be tested scientifically. Despite all these intriguing ideas, it's important to remember that the possibility of extraterrestrial intelligence causing the dimming is still purely speculative. The latest studies have largely ruled out theories involving only solid objects like stars, planets, or asteroid swarms, as well as the idea of an alien megastructure. In 2019, researchers suggested another possibility involving moons. They ran simulations of gas giant planets and their large moons, which could explain the light curve of Tabby's star. In about half of these simulations, the moons were ejected from their planets, and their orbits eventually created a light curve resembling that of the star. As of 2015, a number of telescopes were focusing on Tabby's star, hoping to catch another dimming event. They plan to use powerful telescopes with spectrographs to study the light in greater detail and determine whether the objects causing the dimming are solid, like planets, or made of gas or dust. Further observations are planned using instruments like the Green Bank Telescope, the Very Large Array Radio Telescope, and space telescopes like the Nancy Grace Roman Space Telescope, TESS, and Plato. These tools may help shed more light on the mystery. In 2016, Tabitha Boyajian, the lead researcher behind the first study on Tabby's star, launched a crowdfunding campaign to support continuous monitoring of the star. The campaign raised more than $100,000, which was enough to fund a year of observations using the Las Cumbres Observatory Global Telescope Network. Boyajian also worked with over 50 amateur astronomers from the American Association of Variable Star Observers, who helped provide nearly continuous coverage of the star. A study published in early 2018 suggested that whatever is causing the dimming is likely not a solid object. Instead, it may be space dust, as the dimming affects different wavelengths of light in a way that wouldn't happen if an opaque object were blocking the star. In December of 2018, scientists used the automated planet finder to look for any unusual laser emissions from Tabby's star, which could potentially signal advanced alien technology. While some candidates were found, further analysis showed that these signals were actually coming from Earth, not the star itself. Earlier, in October of 2015, the SETI Institute used the Allen Telescope Array to search for radio signals from possible extraterrestrial civilizations near Tabby's star. However, after conducting an initial 2-week survey, they reported that no evidence of technology-related signals was found. No unusual narrowband or medium-band radio signals were detected, ruling out the possibility that the dimming was caused by alien activity. In the year 2016, astronomers used the Veritas Gamma Ray Observatory to search for something called ultra-fast optical transients coming from distant astronomical objects. These transients are very short bursts of light, only lasting a few nanoseconds. The observatory was designed with a special method that could detect these incredibly quick flashes of light, even if they were extremely faint, about 1 photon, a tiny particle of light, per square meter. This sensitive technique was applied to examine old data about Tabby's star, collected between the years 2009 and 2015. However, despite their efforts, no unusual emissions were found from the star during this search. Then, in May of 2017, another search took place, this time focusing on laser light emissions. This search was related to the earlier one, but again, no signs were found of any technology-related signals coming from Tabby's star. Later, in September of 2017, a new set of tasks was created for a project called SETI at home. SETI stands for Search for Extraterrestrial Intelligence, and the project aims to analyze data that could help us detect signals from alien civilizations. These tasks were based on a previous radio frequency survey of the region around Tabby's star. At the same time, the size of the SETI at home work units was increased, meaning the tasks given to volunteers who used their computers for the project were larger. This change was important because it would likely reduce issues with something called quantization noise, which can make data harder to interpret. In the midst of all these studies, another star called EPIC 200-478,916 and a few other young stars were found to show strange light patterns that resembled the mysterious dips observed in the light from Tabby's star. However, the dips in light from EPIC 200-478,916 were different in a few ways. First, they were much deeper, meaning the star's light dimmed more dramatically than what was observed in Tabby's star. Second, the dips in epoch 200,478,916 occurred in a shorter period of time, while the dips in Tabby's star happened over many years. Also, the young star epoch 200,478,916 was surrounded by a protostellar disk, essentially a disk of gas and dust forming around the star, whereas Tabby's star appeared to be a normal F-type star with no sign of such a disk. The Great Attractor is one of the most mysterious and intriguing phenomena in the universe, a massive region of gravitational pull in intergalactic space. It's thought to be the focal point of a huge collection of galaxies that includes not only our own Milky Way galaxy, but also approximately 100,000 other galaxies. This enormous gravitational force draws galaxies towards it from great distances, and scientists have been working tirelessly to understand its true nature, even though it is incredibly difficult to study directly. Imagine, if you will, an invisible force that has the power to influence entire galaxies over hundreds of millions of light years. That's essentially what the Great Attractor is, a gravitational anomaly located in intergalactic space, right in the middle of the Laniakea supercluster. This supercluster is a massive collection of galaxies, and it spans an enormous distance across the universe. The Milky Way is part of this supercluster, as well as many other galaxies, but the central point of gravitational attraction in this region is still a source of intense curiosity among astrophysicists. The Great Attractor's gravitational pull is so strong that it appears to be causing a massive concentration of mass. Scientists estimate that it could have a mass equivalent to around 10 quadrillion, that's 10,000 trillion, times the mass of our Sun. However, this massive region is hidden from view in a way that makes it hard to observe with traditional telescopes. One of the challenges in studying the Great Attractor is that it lies behind something called the zone of avoidance, which is the part of the sky that is obscured by the Milky Way's own galactic plane. This area is full of dust and gas that blocks visible light, making it nearly impossible to directly observe the Great Attractor using optical telescopes. Despite this, scientists have been able to gather a great deal of information about it by studying the movement of galaxies. Although the Great Attractor itself cannot be seen clearly, its effects can be observed through the movement of galaxies and their clusters. All galaxies in the universe are moving in a general direction, a phenomenon known as the Hubble flow, which means that, on a grand scale, galaxies are moving away from each other. This expansion is a key feature of the universe's evolution, but something peculiar is happening in the region around the Great Attractor. Some galaxies are not just moving away from others, they are being drawn towards it. This deviation from the expected movement is what's known as a peculiar velocity, and it's measured by observing the redshift of light coming from galaxies. Redshift occurs when light stretches as objects move away from the observer, similar to how the sound of a passing car changes pitch. In the case of galaxies near the Great Attractor, scientists have noticed that while these galaxies are still redshifted, their redshifts are not uniform. Instead, the redshift values vary significantly, indicating that these galaxies are not just drifting apart, but are instead being pulled towards something massive. The speed at which these galaxies are moving toward the Great Attractor varies. Some galaxies are moving at speeds as high as 700 kilometers per second, while others are moving at similar speeds, but in the opposite direction. The influence of the Great Attractor is significant enough that even our own Milky Way galaxy is slowly being drawn toward it at a speed of about 600 kilometers per second. The Great Attractor was first identified in the year 1987 by an astronomer named Alan Dressler. He and other scientists were able to identify this massive gravitational anomaly through a combination of redshift surveys. These surveys measured the redshift of galaxies, which allowed astronomers to create detailed maps of peculiar velocities. This data helped scientists realize that there was something significant in the direction of the constellation Centaurus. However, even as early as the 1970s, astronomers were starting to notice signs that something was not quite right in that region of space. In 1973, and again in 1978, the first signs of a deviation from the universe's uniform expansion were reported. This meant that something out there was pulling on the galaxies, causing them to move in a way that was not in line with the rest of the cosmic expansion. Over the next few years, astronomers were able to narrow down the location of this mysterious force, and by 1986, they had determined that it was somewhere between 150 and 250 million light-years away in the direction of the constellations Triangulum Australe and Norma. At the center of the Great Attractor's gravitational region lies the Norma cluster, a massive grouping of galaxies that has been identified through X-ray observations. These galaxies are old, and many of them are in the process of colliding with one another, creating huge bursts of energy, including radio waves. This area of space is home to a rich concentration of galaxies, making it a key focus of astrophysical research. The Norma cluster is the largest and most prominent galaxy cluster in the region of the Great Attractor, but it's not the only one. As astronomers continued to study the area, they discovered that the region was surrounded by other smaller clusters, such as the Pavo 2, Centaurus Crux, and Ca-Isa clusters. These clusters form part of a massive cosmic structure known as the Norma Wall or Great Attractor Wall. The Norma Wall is a vast filament of galaxies that stretches across hundreds of millions of light-years, and it contains some of the most massive galaxy clusters in the universe. This large-scale structure is crucial to understanding the gravitational influence of the Great Attractor. It's not just a collection of isolated galaxies. It's a gigantic, interconnected structure that plays a significant role in shaping the movement of galaxies across vast regions of space. In the early 1990s, astronomers discovered that much of the apparent signal from the Great Attractor could be explained by a phenomenon called the Malmquist bias. This is a statistical effect where more distant galaxies are harder to detect, meaning that astronomers might have overestimated the mass of the Great Attractor based on incomplete data. This led to a reassessment of the region's mass, and by 2005, astronomers confirmed that the Great Attractor was likely only 1/10 as massive as originally thought. The revised data also suggested that the Milky Way's motion was not solely influenced by the Great Attractor, but by an even larger cosmic structure beyond it, the Shapley supercluster. The Shapley supercluster is an even more massive concentration of galaxies, and it's located farther beyond the Great Attractor. This discovery led to the idea of the Shapley attractor, a more massive object that could be responsible for some of the gravitational effects previously attributed to the Great Attractor. The Great Attractor is not an isolated anomaly. It is part of a much larger cosmic structure known as the Laniakea supercluster. This supercluster is a vast collection of 4 main galaxy superclusters, including the Virgo and Hydra Centaurus superclusters, and it spans an astounding 500 million light-years across. Even though the Laniakea supercluster is not dense enough to be gravitationally bound, it remains anchored by the gravitational focal point of the Great Attractor. The local flow of galaxies within the Laniakea supercluster converges at the region around the Norma and Centaurus clusters, which is essentially the position of the Great Attractor. This means that the Great Attractor is not just a local phenomenon, but is part of the larger-scale structure of the universe, shaping the motion of galaxies and influencing the cosmic flow of matter over vast distances. The Great Attractor is a cosmic mystery that has fascinated astronomers and physicists for decades. It represents a powerful gravitational force that influences not only our own galaxy, but also a vast region of space filled with hundreds of thousands of galaxies. Despite the challenges in observing it directly, scientists have pieced together a detailed picture of its effects on the universe. From its discovery in the 1980s to the revelations of the 2005 X-ray surveys, our understanding of the Great Attractor continues to evolve. The insights we've gained about the Great Attractor also reveal much about the larger structures of the universe, such as the Laniakea supercluster, and how they are shaped by the forces of gravity. As we continue to observe the universe and improve our technology, it's likely that new discoveries will shed even more light on this enigmatic force and the role it plays in the cosmic dance of galaxies. The Bootes void, often called the Great Nothing because of the strange and empty nature of its vast expanse, is one of the most intriguing and mysterious phenomena in the cosmos. This enormous region of space, which stretches across an almost unimaginable distance, has captivated astronomers and scientists alike for decades. It is so vast and so empty that when first discovered, it challenged our understanding of the universe itself. To help make sense of this strange phenomenon, let's take a deep dive into its structure, its discovery, and the implications it has for our understanding of space and the universe. The Bootes Void is a vast spherical region of space located in the direction of the Bootes constellation. It is known for its startling emptiness, with very few galaxies in the region compared to what we would expect based on the size of the area. In fact, this void contains only about 60 galaxies, while a similar-sized region elsewhere in the universe could be expected to have approximately 2,000 galaxies. This extraordinary emptiness has earned the Bootes Void the nickname the Great Nothing. The Bootes Void is enormous. It stretches across a region of space with a radius of around 62 megaparsecs, which is about 330 million light-years in diameter. This means that light, which travels at an incredible speed of around 300,000 kilometers per second, or about 186,000 miles per second, would take approximately 330 million years to travel from one side of the Bootes Void to the other. In other words, this region of space is so vast that even light, the fastest thing in the universe, takes more than 300 million years to cross it. For comparison, the distance from Earth to the closest galaxy, the Andromeda Galaxy, is about 2.5 million light-years. The Bootes Void is far larger than that, and yet it contains a startlingly small number of galaxies. It's a region where, instead of stars and galaxies packed densely together like they are in most of the universe, there is mostly empty space. The Bootes Void was first discovered in the year 1981 by Robert Kirshner, an astronomer who was conducting a survey of galactic redshifts. A redshift occurs when the light from distant objects in space shifts toward the red end of the spectrum, which happens when those objects are moving away from us. By studying the redshifts of galaxies, Kirshner was able to identify this massive void in space. The discovery was part of a larger effort to map the structure of the universe, and it revealed a curious anomaly, a huge, nearly empty region of space that seemed to defy the usual patterns of galaxy distribution. Kirshner's discovery was remarkable because it was not the first time astronomers had discovered voids in space, but the Bootes Void was different in its sheer size and emptiness. While smaller voids had been detected before, this one was much larger than any that had been seen, and its scarcity of galaxies raised important questions about the formation and structure of the universe. The center of the Bootes Void lies around 700 million light-years away from Earth. This is incredibly far, but it still places the void within a region of space that astronomers can study. The Bootes Void is located at approximately right ascension 14 hours 50 minutes and declination 46 degrees. These coordinates place it in the Bootes constellation, which is a large constellation in the northern sky. The Bootes Void is not the only interesting feature in this region of space. It also lies near the Hercules supercluster, which is a large cluster of galaxies that forms part of the near edge of the void. To understand why the Bootes Void is so empty, scientists have proposed several theories. One of the leading ideas is that the void formed as a result of the merging of smaller voids. In this way, the Bootes Void is thought to have developed in a similar fashion to the way soap bubbles merge together to form larger bubbles. Over time, these smaller voids combined, and as they did, the number of galaxies in the region was reduced, creating the vast emptiness that we see today. The Bootes Void is not just a random gap in the universe, but rather it is a part of the large-scale structure of the universe, which is made up of galaxies, clusters, and voids. These voids are thought to be a natural feature of the universe's evolution. They form as galaxies and galaxy clusters are drawn toward each other by gravity, leaving vast regions of space between them that contain very few galaxies. As these voids expand over time, the galaxies that once filled them are pulled toward other regions, leaving the voids even emptier. Even though the Bootes Void is largely empty, it is not completely devoid of galaxies. There are still a few galaxies scattered throughout the void, though they are much fewer in number compared to other regions of space. A notable feature is the roughly tube-shaped region that runs through the center of the void. This region contains some galaxies, but it is still vastly underpopulated compared to other parts of the universe. These galaxies may be remnants of the void's formation, or they may have been isolated in the middle of the void as it expanded. The discovery of the Bootes Void raised important questions about the structure of the universe and the way that galaxies are distributed across space. Some scientists worried that the existence of such a massive void might contradict established theories about the evolution of the universe. However, there are no major inconsistencies between the existence of the Bootes void and the lambda-CDM model of cosmological evolution. The lambda-CDM model is a widely accepted theory about the structure and evolution of the universe. It suggests that the universe began as a hot, dense point known as the Big Bang, and over time it has expanded and evolved. Barnard 68 is a dense, cold cloud of gas and dust that completely blocks light from passing through it. While Barnard 68 is indeed dark and mysterious, it is much closer to Earth than the Bootes void. It lies only about 500 light-years away, a tiny fraction of the distance separating us from the Bootes void. Because Barnard 68 blocks light, it appears much darker in images compared to the Bootes void, which, despite being empty, still contains some faint light from distant stars and galaxies. The key difference is that the Bootes void is not a physical object that blocks light, but rather a vast region of empty space where galaxies are scarce. The Bootes void is important for several reasons. First, it helps us understand the large-scale structure of the universe. By studying voids like the Bootes void, astronomers can learn more about how galaxies are distributed and how the universe has evolved over time. The Bootes void also challenges our understanding of cosmic patterns, showing that space can be vast and empty in ways we might not have imagined. Second, the existence of such a large void raises questions about the nature of dark matter and dark energy. These mysterious substances make up most of the universe's mass and energy, and studying voids like the Bootes void can help scientists learn more about how they influence the distribution of galaxies across space. In the fascinating world of radio astronomy, one of the most mysterious phenomena that have caught the attention of scientists and space enthusiasts alike is the fast radio burst, FRB. FRBs are incredibly powerful and brief pulses of radio waves that last for mere fractions of a second to a few seconds. These bursts come from far beyond our galaxy, and their exact cause remains a subject of intense scientific investigation. The energy released by a fast radio burst is staggering. In just 1 millisecond, an FRB can emit as much energy as the Sun does over the course of 3 entire days. Despite this immense energy, the strength of the signal that reaches Earth is astonishingly weak, about 1,000 times weaker than a mobile phone signal from the Moon. This immense contrast between the energy at the source and the weak signal detected on Earth is part of what makes FRBs so intriguing. The first fast radio burst was discovered in 2007 by astronomers Duncan Lorimer and his student David Narkovich when they were reviewing old pulsar survey data. This discovery is now famously known as the Lorimer burst, and it marked the beginning of a new era in radio astronomy. Since that breakthrough, many more FRBs have been detected, and some of these bursts appear to repeat, but in an unpredictable and seemingly random fashion. However, a rare FRB was discovered that repeats in a regular cycle, FRB 180916, which pulses every 16.35 days. The majority of FRBs detected so far have come from outside of our Milky Way galaxy, though in April 2020, astronomers made a historic discovery. The first FRB within our galaxy was detected by the CHIME radio telescope. Just 1 year later, in June 2021, astronomers announced that they had detected more than 500 FRBs from deep space over the course of a single year, highlighting how active this phenomenon is in the universe. When FRBs are polarized, it suggests that they are being emitted from a source located within a very powerful magnetic field. As for the origins of these bursts, astronomers have put forward various theories. These range from the idea that they might be caused by rapidly spinning neutron stars, the presence of black holes, or even the activity of extraterrestrial civilizations. In 2020, scientists narrowed down the possible causes of FRBs to include compact object mergers and magnetars that result from the collapse of a star's core during a supernova. Interestingly, in 2022, a neutron star was proposed as the source of an unusual FRB that produced periodic bursts lasting more than 3 seconds. One of the most important discoveries in the study of FRBs came in 2012 when astronomers identified the first repeating FRB source called FRB 121102. This discovery, along with the localization and study of the source in 2017, greatly advanced our understanding of these mysterious signals. The FRB 121102 originates from a galaxy that is about 3 billion light-years away and is located in an extreme cosmic environment. Another significant discovery occurred in 2019 when scientists identified the first host galaxy for a non-repeating FRB, FRB 180924. This galaxy is much more ordinary compared to the extreme environment of FRB 121102 and is nearly as large as the Milky Way. In August of the same year, astronomers also detected 8 more repeating FRBs, adding to the growing catalogue of these fascinating events. In January 2020, astronomers pinpointed the location of another repeating FRB, FRB 180916, bringing even more clarity to the study of FRBs. In April 2020, astronomers made another groundbreaking discovery when they detected 2 fast radio bursts, FRB 2000 and 200428, that came from the same region of the sky as the Magnetar SGR 1935 plus 2154. Although these bursts were not as bright as some of the other fast radio bursts observed in the past, their proximity made them the most powerful FRBs ever detected at the time. They reached a peak flux that was comparable to the brightness of famous radio sources like Cassiopeia A and Cygnus A at the same frequencies. This discovery was significant because it provided solid evidence linking magnetars to the origin of some fast radio bursts, though scientists are still unsure about the exact cause of these bursts. Further research has since supported the idea that magnetars could be closely connected to the generation of FRBs. Fast forward to October 13, 2021, when astronomers reported the detection of hundreds of FRBs coming from a single system. This discovery added yet another layer of complexity to the study of these bursts, suggesting that they may be more common and diverse than previously thought. In 2024, an international team of astrophysicists from INAF, National Institute for Astrophysics, conducted an in-depth study of FRB 20201124A, one of only 2 known persistent FRBs. Located about 1.3 billion light-years away, this FRB was found to be originating from a binary system where 2 stars are closely interacting. The intense gravitational forces in this system cause a high accretion rate, which in turn blows a plasma bubble responsible for the continuous radio emissions observed as the persistent FRB. The bubble is situated in a star-forming region, providing a new perspective on the conditions that could give rise to these mysterious bursts. The discovery of FRB 101024, known as the Lorimer burst in 2007, was the first fast radio burst to be described in scientific literature. This burst was found in archived data from the Parkes Observatory, collected on July 24, 2001. Following this, a number of other FRBs were identified in previously recorded data. On January 19, 2015, astronomers made another milestone discovery when they observed an FRB live for the first time using the Parkes Observatory in Australia. Since then, the CHIME, Canadian Hydrogen Intensity Mapping Experiment radio telescope, which became operational in 2018, has played a crucial role in detecting many FRBs, including the first FRB observed within the Milky Way in April 2020. In January 2025, astronomers made an extraordinary discovery when they detected radio waves from a galaxy that is located approximately 2 billion light-years away. This galaxy is believed to be more than 11 billion years old, suggesting that the phenomenon of fast radio bursts may have been occurring since the early stages of the universe. Interestingly, these FRBs are associated with a galaxy that was once thought to be dead, raising new questions about the activity and evolution of galaxies over time. Fast radio bursts are characterized by their brief, millisecond-long flashes of radio waves that span a wide range of frequencies. These bursts are incredibly bright and usually appear as a single spike of energy, with no gradual build-up or decline. They are detected in various parts of the sky, and their locations are not confined to the plane of our Milky Way galaxy. However, the locations of known FRBs are influenced by the areas of the sky that observatories are able to observe. Many of the detected FRBs have radio frequencies around 1400 MHz, but a few have been detected at lower frequencies, between 400 and 800 MHz. The component frequencies of each burst are delayed by different amounts depending on the wavelength, and this delay is measured using a value known as the dispersion measure, DM. As a result, the signal from an FRB appears to sweep downward in frequency, with longer wavelengths experiencing more delay than shorter ones. To determine the distance to the FRBs they have observed, scientists have used an interferometer called UTMOST, which has established a lower limit of at least 10,000 kilometers for the distance to the FRBs it has detected. This distance is significant because it rules out the possibility that the bursts originate from sources on Earth, further supporting the idea that FRBs are an astronomical phenomenon. Fast radio bursts, FRBs, are incredibly intense bursts of radio waves that have pulse dispersion measurements greater than 100 parsecs per cubic centimeter, which is much larger than what we would expect from a source located within the Milky Way galaxy. This large dispersion is consistent with the idea that these bursts travel through an ionized plasma. Furthermore, FRBs don't seem to come from any specific direction, suggesting that they are not coming from our galaxy's plane. This has led scientists to propose that they are likely from outside our galaxy. Because these bursts are so isolated and unpredictable, scientists have not yet reached a consensus on what could be causing them. As of 2022, there is still no single widely accepted explanation for their origin. One theory that has gained attention is the idea that magnetars, a type of neutron star with a very strong magnetic field, could be responsible for generating these bursts. However, this theory, along with others, is still under investigation. Scientists have also concluded that the sources of these bursts must be incredibly small, no more than a few hundred kilometers in size, given that the bursts themselves last only a few milliseconds. The bursts travel at the speed of light, which is about 300 kilometers per millisecond, so if the sources were larger than 1,000 kilometers, the bursts would need a very complex mechanism to ensure they remain so brief. If the bursts are indeed coming from great distances in space, the energy required for such an event must be immense. In 2024, a method was proposed to measure the size of the emission region of these bursts by using a scattering screen in the host galaxy. Later that same year, a burst recorded previously in 2022, FRB 2022-10122A, was found to have an emission region smaller than 30,000 kilometers using this method. One theory is that these bursts could be the result of a collision between extremely dense objects, such as the merging of black holes or neutron stars. Another idea is that FRBs might be linked to gamma-ray bursts, which are also high-energy events in space. Some have even speculated that these signals could be coming from an advanced extraterrestrial civilization, as the bursts could be a form of techno-signature, a signal of technology. This speculation was not unlike the early theory about pulsars when they were first discovered, where the regular pulses were initially thought to come from a distant alien civilization. This led to the pulsar being nicknamed LGM-1, short for Little Green Men. In 2007, just after the discovery of the first FRB, the idea was proposed that these bursts might be related to hyperflares from magnetars. By 2015, several studies were published that supported this theory. The first FRB originating from the Milky Way was identified in 2022 and came from a magnetar named SGR 1935+2154, which further suggests that magnetars could be one source of FRBs. Another possible source could be extremely energetic supernovae, which are massive stellar explosions. In 2013, the idea of blitzars, a type of short-lived, high-energy event, was proposed as a potential explanation for FRBs. In 2014, scientists suggested that the collapse of pulsars caused by dark matter could lead to the expulsion of the pulsar's magnetosphere, which could result in the fast radio bursts. That FRBs might be the result of the explosive decay of axion mini-clusters, which are small, hypothetical objects in space. Yet another theory points to cosmic strings, which are theoretical defects in spacetime, interacting with the plasma in the early universe and creating these bursts. In 2016, scientists proposed that the collapse of the magnetospheres of a specific type of black hole, called Kerr-Newman black holes, might explain the afterglow seen in some FRBs, as well as a weak gamma-ray transient observed shortly after the gravitational wave event GW150914. If FRBs do indeed originate from black hole explosions, they might also represent the first direct evidence of quantum gravity effects. In early 2017, another theory was proposed, suggesting that the strong magnetic fields near a supermassive black hole might destabilize a pulsar's magnetosphere, releasing energy that powers the FRBs. One FRB, known as FRB 121102, has been observed to repeat multiple times, sparking numerous hypotheses about its origin. One explanation is that the bursts might be related to a phenomenon called superradiance, where large quantum mechanical states could produce coherent emissions in environments such as active galactic nuclei. These environments might also explain other characteristics of FRBs, such as their high event rate, repeatability, and varying intensity profiles. In July of 2019, astronomers made an important observation, suggesting that non-repeating FRBs might not be one-time events as previously thought. Instead, they may be repeaters whose subsequent bursts simply haven't been detected yet. It was also proposed that these bursts might originate from nearby stellar flares. In 2022, a particularly intriguing FRB was observed with multiple periodic peaks lasting over 3 seconds. This burst was thought to possibly originate from a neutron star. Fast radio bursts are typically named after the date they were recorded, in a format like FRB YYMDD, with a letter added to distinguish between multiple bursts recorded on the same date. The name refers to the source of the burst, rather than the burst itself, so multiple bursts from the same source, such as FRB 121102, do not receive new names. The very first FRB ever detected, known as the Lorimer burst, was discovered in 2007 by Duncan Lorimer from West Virginia University. Lorimer had asked his student David Narkovic to go through some old data from 2001, which had been collected by the park's radio dish in Australia. Upon analysis, they found a burst of radio waves that was less than 5 milliseconds long, occurring on July 24, 2001. The burst came from a point in the sky about 3 degrees away from the small Magellanic Cloud. The characteristics of this burst made it clear that it didn't come from the Milky Way or the small Magellanic Cloud, and it was therefore named the Lorimer burst. Based on current models of the free electron content in the universe, it is thought that this burst was located less than 1 gigaparsec away. Additionally, the fact that no further bursts were detected during 90 hours of additional observations suggested that it was a one-time event, possibly from a supernova or the merger of relativistic objects. It is believed that there are probably hundreds of similar events occurring every day in the universe, and if we could detect more of them, they might help us learn more about the cosmos. In 2010, a set of 16 similar pulses was detected by the park's radio telescope, but these were later shown to have been of terrestrial origin. They were caused by a microwave oven's magnetron tube when the door was opened during the heating cycle. In 2015, an FRB called FRB 110523 was discovered in data collected by the Green Bank telescope in 2011. This was the first FRB for which linear polarization was observed, allowing scientists to measure Faraday rotation. The burst's dispersion delay indicated that it likely originated from outside our galaxy, possibly up to 6 billion light-years away. Victoria Caspi from McGill University has estimated that as many as 10,000 fast radio bursts could occur every single day across the entire sky. In 2012, another FRB, known as FRB 121102, was observed with the Arecibo radio telescope in the direction of the Auriga constellation. This observation confirmed that FRBs originate from outside the Milky Way galaxy thanks to a phenomenon known as plasma dispersion. In November 2015, astronomer Paul Schultz, working at McGill University in Canada, made an intriguing discovery while reviewing data collected months earlier in May and June of that year. The data, gathered by the Arecibo radio telescope, contained 10 fast radio bursts, FRBs, that did not repeat in a regular pattern. These bursts were unlike any others detected before, and they closely resembled the characteristics of a burst first observed in 2012, known as FRB 121102. These new bursts, like the original one, had dispersion measures and sky positions that aligned with the earlier burst, suggesting a shared origin. The 10 radio bursts showed a plasma dispersion measure 3 times higher than would be expected if they were originating from within our own Milky Way galaxy. This finding was significant because it made it unlikely that these signals were the result of a one-time catastrophic event, such as a collision between 2 neutron stars. Instead, the researchers speculated that these bursts could be coming from a young, rapidly spinning neutron star, also known as a pulsar, or from a highly magnetized neutron star known as a magnetar. Another possibility was that the bursts were emitted from pulsars moving through asteroid belts or from an intermittent overflow of material in a neutron star-white dwarf binary system. Fast forward to December 16, 2016, when scientists announced that 6 additional FRBs had been detected coming from the same region of space as the original FRB 121102. These included 1 burst recorded on November 13th, 2 bursts on November 19th, and another one on December 8th of that year. By January 2019, it was clear that this was one of only 2 instances in which FRBs had been observed multiple times from the same location in the sky, making it even more mysterious. FRB 121102, situated at least 1,150 astronomical units, AU, from Earth, was far too distant to be a signal from human-made sources, and scientists were now certain it was of extragalactic origin. By April 2018, new theories were emerging regarding the nature of FRB 121102. It was hypothesized that the bursts could be coming from a dwarf galaxy roughly 3 billion light-years away from Earth, possibly associated with a low-luminosity active galactic nucleus, or even from an unknown type of extragalactic source. Another suggestion was that a young neutron star might be energizing a supernova remnant in the galaxy. On August 26, 2017, a team of astronomers, using data from the Green Bank telescope, detected 15 more repeating fast radio bursts emanating from the same location as FRB 121102, with frequencies ranging from 5 to 8 GHz. The researchers noted that FRB 121102 seemed to be in a heightened state of activity, and they recommended further observations, especially at higher radio frequencies. These new bursts exhibited high polarization and underwent Faraday rotation, a phenomenon where the plane of polarized light rotates as it passes through a hot plasma with a very strong magnetic field. This rotation was measured by a value called the rotation measure, RM, which for FRB 121102 was about 500 times higher than any other FRB observed so far. Because FRB 121102 was a repeating source, scientists ruled out the possibility that it came from a one-time catastrophic event. A hypothesis, first put forward in January 2018, proposed that these repeating bursts could be originating from a dense stellar core, such as a neutron star, located near a powerful magnetic field, possibly one near a massive black hole or embedded in a nebula. In April 2018, an astonishing discovery was made. FRB 121102 produced a series of 21 bursts within a 1-hour period. Later that same year, in September, a further 72 bursts spanning 5 hours were detected using a convolutional neural network, an advanced form of artificial intelligence. These bursts were more frequent than anticipated, prompting the team to continue their investigation into the behavior of FRB 121102. September 2019 brought even more surprises. The 500-meter aperture spherical telescope, FAST, reported the detection of 20 additional bursts, including one on September 3, 2019. As researchers studied the pattern of these bursts, it became evident that FRB 121102 exhibited a consistent cycle of activity. By June 2020, astronomers from Jodrell Bank Observatory had determined that the bursts followed a repeating cycle of approximately 157 days, with active bursts lasting for 90 days, followed by a quiet period lasting around 67 days. This periodic behavior suggested that the bursts could be related to the orbital motion of a massive star, neutron star, or black hole. Further observations made by FAST in August 2020 showed a more refined periodicity, with bursts detected over the span of 2 hours on August 17, 2020. These bursts helped to tighten the timeline for the repeating cycle to 156.1 days. This discovery opened up new possibilities for understanding the mechanisms behind these mysterious events. In 2022, FAST detected over 300 bursts from FRB 121102 during August and September, adding to the growing evidence that this particular source was extremely active. Then, in July 2023, another set of 19 bursts were recorded by the Green Bank telescope, with 8 of them being exceptionally brief, lasting only 5 to 15 microseconds. These were the shortest bursts ever detected from this source, further deepening the mystery surrounding FRB 121102. But the story of fast radio bursts didn't begin with FRB 121102. In 2013, researchers identified 4 other bursts that supported the idea that FRBs could originate from extragalactic sources. The following year, in 2014, another significant discovery was made when FRB 140514 was detected live and was found to be polarized, with 21% of the burst being circularly polarized. On April 18, 2015, a burst known as FRB 150418 was detected by the Parkes Observatory in Australia. Within hours, multiple telescopes, including the Australia Telescope Compact Array, observed what seemed to be an afterglow of the burst, which lasted for 6 days before fading away. The Subaru telescope was used to identify the host galaxy and measure its redshift, allowing scientists to estimate the distance to the burst. However, the initial assumption that this afterglow was related to the FRB was soon questioned. By April 2016, further analysis revealed that the afterglow was not related to the FRB, but instead originated from an active galactic nucleus, AGN, powered by a supermassive black hole, which was emitting dual jets of energy. The confusion arose because the afterglow did not fade away as expected, leading scientists to conclude that it was an unrelated phenomenon tied to the AGN rather than the FRB. Meanwhile, the upgraded Molonglo Observatory Synthesis Telescope, YUTMOST, located near Canberra, Australia, reported the discovery of 3 more FRBs. A 3-part survey conducted over a 6-month period in 2015 and 2016 found 3 FRBs at a frequency of 843 MHz. These FRBs were detected with a relatively narrow beam, which provided a less precise measurement of their dispersion. In 2017, a short survey using part of the Australian Square Kilometre Array Pathfinder, ASCAP, observed 1 FRB over the span of 3.4 days. This burst, known as FRB 170107, was particularly bright, with a fluence of 58 plus or minus 6 Jansky milliseconds. According to researchers Anastasia Fielkov and Abraham Loeb, FRBs might be occurring as often as once per second. Previous studies had not been able to confirm this level of frequency, but this idea has sparked further research into the potential prevalence of these mysterious events. In March 2018, the Parkes Observatory in Australia reported 3 more FRBs. One of them, known as FRB 180309, had the highest signal-to-noise ratio ever recorded, reaching a remarkable 411. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, which began operations in September 2018, is another important player in the search for FRBs. Though its primary goal is to observe the hydrogen content in the universe, CHIME also detected hundreds of fast radio bursts as a secondary objective. One of its key discoveries was FRB 180725A, which was the first FRB detected at a frequency below 700 MHz, reaching as low as 580 MHz. In October 2018, astronomers reported the detection of 19 new non-repeating FRBs by the Australian Square Kilometre Array Pathfinder. These included 3 bursts that had smaller dispersion measures than those previously observed. On January 9, 2019, astronomers announced the discovery of a second repeating FRB source, named FRB 180814. 6 bursts were detected between August and October of 2018, and these signals appeared to be coming from a single location in the sky. This discovery was made during CHIME's pre-commissioning phase and it hinted at the existence of a substantial population of repeating FRBs. It also suggested that CHIME would continue to make more such detections in the future. The discovery of fast radio bursts, FRBs, has led to some interesting speculation in the media. Some outlets have suggested that these mysterious signals could be evidence of extraterrestrial intelligence, although this idea has been explored by a few scientists before, particularly in relation to other FRBs. However, this possibility was not mentioned by the team responsible for discovering FRB 1818-14. One of the most significant discoveries in this area was FRB 1818-916, also known by its more formal name, FRB 1818-916. This repeating FRB was identified by the Canadian Hydrogen Intensity Mapping Experiment, CHIME, and after further studies was found to originate from a medium-sized spiral galaxy located about 500 million light-years away. This made it the closest FRB ever detected up to that point. What set FRB 1818-916 apart was its regular periodicity, which was previously unseen in other FRBs. The bursts from this signal appeared in a consistent pattern. They clustered into a period lasting around 4 days, followed by a dormant phase that lasted about 12 days, completing a full cycle of roughly 16 1/3 days. This periodic nature of the FRB was a groundbreaking observation. In February of the year 2020, additional studies using several instruments, including the Swift X-ray Telescope, XRT, and Ultraviolet Optical Telescope, UVOT, helped researchers better understand the behavior of FRB 1818-916. Similar observations were carried out in February by the Sardinia Radio Telescope and the Medicina Northern Cross Radio Telescope, as well as by the Galileo Telescope in Asiago. Further studies were conducted using the Chandra X-ray Observatory in December of 2019, but no significant X-ray emissions were found either at the location of FRB 1818-916 or in the host galaxy. On the 6th of April, 2020, follow-up studies were conducted by the Global Master Net, and reports of these findings were published in the Astronomer's Telegram. Further observations were made in August of 2021. Another intriguing case involved FRB 1818-1112, which remained undisturbed despite passing through the halo of an intervening galaxy. This observation sparked a range of questions about how such a phenomenon could occur and why the signal was seemingly unaffected. One of the most exciting discoveries was FRB 1818-924, which became the first non-repeating FRB to be traced back to its source. This FRB was found to originate from a galaxy located 3.6 billion light-years away from Earth. This galaxy is nearly as large as the Milky Way, but its host galaxy was much older and less active than the one that housed FRB 121102, which had been previously linked to a Magnetar, a type of neutron star known for its intense magnetic field. In this case, however, the galaxy emitting FRB 1818-924 was not an active site of star formation. Astronomers had to conduct extensive scans over vast areas of sky using 36 telescopes to detect this FRB. Once the signal was detected, further observations were made using the Very Large Telescope, the Gemini Observatory in Chile, and the W.M. Keck Observatory in Hawaii. These follow-up studies revealed key details about the distance to the source and the characteristics of the host galaxy, which then enabled scientists to study the composition of the intergalactic medium, the matter that exists between galaxies. In June of 2019, Russian astronomers reported the detection of 9 FRB events, including FRB 151125, the third repeating FRB ever discovered. These signals were traced back to the Andromeda Galaxy and the Triangulum Galaxy through an analysis of archived data collected between July of 2012 and December of 2018. This data was gathered using the BSA LPI Large Phased Array Radio Telescope at the Pushchino Radio Astronomy Observatory. Another significant discovery came in May of 2019 with FRB 190520. This FRB was observed by the 500-meter Aperture Spherical Radio Telescope, FAST, and was localized using the real-fast system at the Carl G. Jansky Very Large Array, VLA. Optical observations were then made using the Palomar 200-inch Hale telescope, which revealed that the signal came from a host dwarf galaxy located at a redshift of 0.241. This was the second FRB to be linked to an associated persistent radio source, PRS, which indicated that the environment surrounding the source of the FRB was dense, magnetized, and highly turbulent. Later in June of 2022, it was confirmed that FRB 2019050b, which had been detected earlier, was also a repeating FRB. By May of 2023, FRB 2019050b showed multiple bursts, which suggested that magnetic fields were reversing at the source. FRB 190523, another non-repeating FRB, was discovered in July of 2019. This signal was traced to a region just a few arcseconds in size, which contained a single massive galaxy located about 8 billion light-years away, with a redshift of 0.66. This discovery added to the growing understanding of the diversity of FRBs and their sources. In August of 2019, the Chime Fast Radio Burst collaboration reported the detection of 8 more repeating FRB signals. By December of that same year, Australian astronomers from the Molonglo Observatory Synthesis Telescope, MOST, had detected FRB 191223 in the Octans constellation. Shortly after, on the 31st of December, another FRB, FRB 191228, was detected in the Piscis Austrinus constellation using the Australian Square Kilometre Array Pathfinder, ASCAP. In early 2022, astronomers proposed that a globular cluster within the M81 galaxy, a grand design spiral galaxy about 12 million light-years away, might be the source of the repeating FRB 202000120e. This discovery added to the growing list of sources tied to repeating FRBs. In September of 2023, astronomers reported the discovery of FRB 202000317a, which was detected by the FAST telescope in archival data. This particular FRB was one of the faintest to be detected so far, according to the astronomers who reported it. The FRB was localized to a specific region in the sky, providing valuable data for further investigation. Another notable discovery occurred on the 28th of April 2020, when astronomers from Chime detected a bright radio burst originating from the Galactic Magnetar SGR 1935+2154, located approximately 30,000 light-years away in the Vulpecula constellation. This burst, referred to as FRB 200428, was significant because it was the first FRB detected inside the Milky Way and was directly linked to a known source, a magnetar. The connection between this burst and other FRBs at extragalactic distances strongly supported the theory that magnetars are responsible for generating these mysterious signals. In January of 2024, astronomers reported that the source of FRB 202000610a was a rare blob-like group of galaxies, further expanding the variety of sources linked to FRBs. Meanwhile, on the 24th of September, 2 new FRBs were detected by the Parkes Radio Telescope, FRB 200914 and FRB 200919. Later, upper limits on low-frequency emissions from FRB 200914 were reported by the Square Kilometre Array Radio Telescope project. Throughout 2021, numerous follow-up observations were made, with astronomers detecting multiple bursts from several repeating FRBs, including FRB 20201124a. The burst activity was so high that astronomers reported more than a dozen bursts over the course of the year. In early 2022, further investigations into FRB 20201124a suggested that its source might be a binary system containing a magnetar and a B-star, a type of massive star that is often associated with strong magnetic fields. In April of 2021, 2 new bursts, FRB 202104001a and FRB 202104002a, were detected by astronomers at the Australian Square Kilometre Array Pathfinder. These were believed to be repetitions of FRB 20201124a. further confirming the activity of this repeating FRB. By the end of June 2021, the Molonglo Observatory Synthesis Telescope, UTMOST, detected another FRB, FRB 210630A, at a position that was likely to be linked to a previously known region in the sky. This was another significant addition to the expanding catalogue of FRBs. Each of these discoveries has contributed to our growing understanding of fast radio bursts, from their mysterious origins to the diverse environments in which they occur. The study of these enigmatic signals continues to be one of the most exciting areas of research in modern astronomy. Dark matter is one of the biggest mysteries in the universe. Scientists believe it exists, but they can't see it, touch it, or directly detect it. The reason? Dark matter does not interact with light or any other form of energy that we can measure. However, something unseen is clearly affecting the way galaxies move, the way gravity behaves, and even the way light bends around massive objects. These strange effects suggest there is a lot more matter in the universe than we can actually observe. We can see dark matter's influence in many ways. For example, galaxies spin so fast that based on the visible matter alone, they should fly apart, but they don't. This suggests there is some unseen mass holding them together. Another clue comes from gravitational lensing, when light from distant galaxies bends as it passes massive objects like clusters of galaxies. The way this light bends tells us that there is far more mass present than we can actually see. Dark matter also plays a role in shaping the universe's large-scale structure and even appears to have influenced the leftover radiation from the Big Bang, known as the cosmic microwave background. Scientists use a model called the lambda cold dark matter, lambda CDM model, to describe the makeup of the universe. According to this model, about 5% of the universe is made of normal matter, the kind of matter we can see and touch, like stars, planets, and people. Around 26.8% is dark matter, an invisible form of matter that only interacts through gravity. The remaining 68.2% is dark energy, a mysterious force causing the universe to expand faster and faster. In other words, dark matter makes up about 85% of all the mass in the universe. When combined with dark energy, these two unknown forces account for 95% of everything that exists. This means that everything we see, stars, galaxies, planets, and even ourselves, makes up only a tiny fraction of the universe. Despite years of searching, scientists still don't know exactly what dark matter is. Since it does not emit or reflect light, we can't observe it directly. However, based on the way it behaves, researchers think it might be made of tiny, unknown particles. The leading candidates include weakly interacting massive particles, WIMPs. These are hypothetical particles that could be heavy but barely interact with normal matter except through gravity. Axions. These are extremely light particles that might be able to explain dark matter while also solving some mysteries in particle physics. Primordial black holes. Some scientists wonder if dark matter could be made of black holes that formed in the early universe, before stars and galaxies existed. Dark matter is also categorized based on how fast its particles move, cold, warm, or hot. Most experts believe dark matter is cold, meaning its particles move slowly, allowing them to clump together and help form the structures of the universe over time. Most astrophysicists are convinced that dark matter exists because of the overwhelming evidence. However, a few scientists have suggested an alternative idea. What if our understanding of gravity is incomplete? Some researchers believe that instead of searching for invisible matter, we should modify the laws of gravity. The most famous alternative theory is modified Newtonian dynamics, MOND, which suggests that gravity behaves differently on very large cosmic scales. Others propose even more radical ideas about how gravity might work in ways we don't fully understand. While these theories are interesting, none of them can fully explain all the observations that dark matter accounts for. This means that even if gravity does need some adjustments, dark matter still seems to be an essential part of the universe's structure. The idea that space might contain hidden matter has been around for more than a century. Some of the brightest minds in science contributed to this discovery, beginning in the late 19th century. 1884. British scientist William Thomson, better known as Lord Kelvin, studied the movements of stars around the Sun. He noticed that their motion didn't quite make sense unless there was some unseen mass affecting them. Though he didn't call it dark matter, his work hinted at the idea that space might contain invisible mass. 1906, French mathematician Henri Poincaré was the first to use the term dark matter, or matière obscure. He suggested that some mass in the universe might be hidden, though he believed it was less than the visible matter we could see. 1922, Dutch astronomer Jacobus Kapteyn studied how stars move and suggested that an unseen force could be influencing them. 1930, Swedish scientist Knut Lundmark realized that the universe seemed to have far more mass than what telescopes could observe. This was a major step in recognizing that the visible universe was only part of the picture. 1932, Dutch astronomer Jan Oort studied the movement of stars in our galaxy and suggested that there was more mass than what was visible. However, his measurements were not entirely accurate, and further research was needed. 1933, Swiss astrophysicist Fritz Zwicky made a major breakthrough. While studying the Coma cluster, a large group of galaxies, he noticed that the galaxies were moving much faster than expected. Based on visible matter alone, they should have flown apart, but something unseen was holding them together. Zwicky estimated that the cluster had about 400 times more mass than what was visible. He called this unseen mass Dunkelmaterie, or dark matter, UC. His calculations were off, but his idea was correct. The universe contained much more mass than we could observe directly. At the time, Zwicky thought dark matter was simply normal matter that didn't emit light, rather than an entirely different type of substance. Still, his work laid the foundation for modern dark matter research. As time went on, more scientists found clues that pointed to dark matter's existence. 1939, astronomer H.W. Babcock studied the rotation of the Andromeda Galaxy, the closest spiral galaxy to Earth. He found that the stars on the galaxy's outer edges were moving much faster than expected. This suggested that an unseen force, possibly dark matter, was influencing their movement. 1940, Jan Oort made another important discovery when he observed a galaxy called NGC 3115. He found that it was surrounded by an invisible mass, providing more evidence that galaxies contained hidden matter. Since these early discoveries, scientists have gathered even more evidence that dark matter is real. Today, advanced telescopes and space observatories continue to study its effects, but the true nature of dark matter remains one of the greatest mysteries of modern science. The idea of dark matter really started gaining attention in the 1970s. Various scientific findings were combined to suggest that galaxies might be surrounded by huge, invisible layers of matter. In 1974, two separate research teams, one from Princeton, New Jersey, led by Jeremiah Ostreicher, Jim Peebles and Amos Yahill, and another from Tartu, Estonia, led by Jan Einasto, N. Saar, and Ants Karsik, reached the same conclusion independently, making the theory stronger. One important clue that pointed to the existence of these unseen galactic layers was how galaxies spin. Both optical and radio astronomy played a big part in these discoveries. Vera Rubin and Kent Ford, using a new tool called a spectrograph, made more precise measurements of how fast the edges of spiral galaxies were moving, revealing surprising results in the rotation patterns. At the same time, radio astronomers used better radio telescopes to study the 21-centimeter wavelength of hydrogen gas in nearby galaxies. Unlike starlight, which is only visible in the central areas of galaxies, hydrogen gas spreads much farther out. This helped astronomers observe rotation speeds at much greater distances, giving them a clearer idea of a galaxy's total mass. Early studies of the Andromeda Galaxy, using giant telescopes like the 300-foot Green Bank telescope and the 250-foot Jodrell Bank dish, showed that the hydrogen rotation pattern did not match what was expected based on Kepler's laws, which explain how objects should move around a central mass. As technology got better, more accurate tools allowed for even deeper studies. In 1975, Roberts and Whitehurst expanded research by measuring Andromeda's rotation speed all the way out to 30 kiloparsecs. Their findings showed that the galaxy's rotation curve stayed flat even at far distances. This was important because it suggested there was much more unseen mass beyond what could be detected with regular telescopes. Their results, displayed in graphs, combined optical data with the new hydrogen data, clearly showing the unexpected flatness of the galaxy's outer rotation curve. The solid line in the graph represented the optical data from stars, while the other line showed the total mass, which kept increasing even in the farthest parts of the galaxy. At the same time, scientists were creating even better ways to study galaxies. Using networks of radio telescopes working together, called interferometric arrays, researchers like Rogstad and Shostak in 1972 mapped the hydrogen rotation curves of 5 spiral galaxies. They found that all of these galaxies had flat rotation curves, meaning that the mass in the outer parts was much larger than what was visible from stars and light. By the late 1970s, most astronomers agreed that dark matter halos probably existed around galaxies, making it one of the biggest mysteries in space research. In the 1980s and 1990s, many studies added more proof that dark matter was real. One major study, done by Persic, Salucci, and Stell in 1996, closely examined 967 spiral galaxies and found strong evidence supporting the presence of dark matter. Other signs included unusual effects like gravitational lensing, where galaxy clusters bend light from objects behind them, the spread of hot gas in galaxies and clusters, and small temperature changes in the cosmic microwave background, the faint radiation left over from the Big Bang. Today, most scientists believe that dark matter is made of particles that have not yet been discovered, and these particles are unlike anything we currently know. The search for these mysterious particles has become one of the biggest challenges in physics, with many researchers using different methods and experiments to try to solve the mystery. Simply put, when scientists talk about matter in the universe, they mean anything that contributes to the total energy and its density changes in a certain way as the universe expands. Specifically, it decreases as the universe gets bigger, meaning the farther it stretches, the thinner matter becomes. This is different from radiation, which fades away even faster. Its energy weakens as the universe grows, following a pattern called the inverse fourth power of expansion. On the other hand, the cosmological constant behaves differently. It stays the same no matter how much the universe expands, meaning its energy density never changes. This difference in how matter, radiation, and the cosmological constant behave is due to something called radiation redshift. Imagine the universe expanding. If its size doubles, the scale factor of expansion also doubles. Because of this, the energy of things like the cosmic microwave background, the leftover radiation from the Big Bang, weakens, since each photon, a tiny particle of light, has to stretch out over a larger space, losing energy. The same happens to certain fast-moving particles like early neutrinos, which lose energy in a similar way. However, the cosmological constant, since it is a property of space itself, does not change no matter how much the universe grows. As for dark matter, this term usually refers to parts of the universe that cannot be seen but still have mass and follow the same rules as normal matter. However, in a more specific sense, dark matter describes a special kind of invisible matter that is not made of the usual particles we know, excluding something called missing baryons. Depending on the situation, the meaning of dark matter can change. The arms of spiral galaxies spin around their center, and as you move farther out, the amount of visible mass in the galaxy gets smaller. If all of a galaxy's mass were visible, it would act like a simple system where most of the mass is in the center and objects orbit it, similar to how planets move around the sun in our solar system. Based on Kepler's third law, we would expect objects farther from the center to move more slowly, just like planets in our solar system orbit the sun at slower speeds the farther they are from it. But that's not what happens in galaxies. Instead, the rotation speeds of stars and gas stay the same, or even increase as you move outward from the center. To explain this strange observation, it seems clear that the way mass is spread out in spiral galaxies is different from the solar system. Specifically, there may be a large amount of unseen non-glowing matter, what we call dark matter, on the outer edges of the galaxy. In connected systems like galaxies, the stars also follow a rule called the virial theorem, which helps explain how mass is spread out in a system based on the speeds of the stars. When astronomers study how fast stars move in systems like oval-shaped galaxies or dense groups of stars, they can use this rule to figure out how mass is arranged. However, in many cases, The measured speeds don't match what we'd expect based on the amount of visible mass in the system, even when we consider the complex paths the stars follow. Much like with the spinning movement of galaxies, the most reasonable explanation for this mismatch is that there's more unseen matter involved. Again, dark matter. Groups of galaxies are important for studying dark matter because we can measure their mass in 3 different ways: by looking at the range of speeds at which the galaxies in the group move, by studying the X-rays given off by the hot gas inside the group. By analyzing these X-rays, we can find the temperature and thickness of the gas, which helps us calculate the pressure. Using the balance between gravity and pressure, we can figure out the total mass of the group. Through gravitational lensing, where the mass of the group bends light from farther objects. This lets us measure the group's mass without needing to directly observe the movement of the galaxies. All 3 of these methods lead to the same result. Dark matter makes up about 5 times the mass of all the visible matter in these groups. One interesting result of Einstein's theory of general relativity is something called gravitational lensing. This happens when huge objects, like galaxies or groups of galaxies, sit between a light source and the observer. These massive objects act like a lens, bending the light that passes through them, making the light from the source appear distorted. The key point is that gravitational lensing only depends on mass. It doesn't matter what the mass is made of. The more massive an object is, the stronger the bending of light will be. For example, imagine a group of galaxies lying between a very distant object like a quasar and us. In this case, the galaxies in the group will bend the light from the quasar, making it look different. When we talk about strong lensing, we mean the way the light from background galaxies can be bent into arc shapes as it passes through a massive object's gravitational field. This has been seen around many faraway galaxy groups, including one known as Abell 1689. By studying the shape of these arcs, scientists can figure out the mass of the galaxy group causing the bending. In the weak lensing case, the bending is much smaller, and galaxies don't turn into arcs. Instead, we see tiny distortions in the shapes of galaxies. By looking at these slight changes, scientists can learn about how dark matter is spread across the universe. The patterns of mass and light from these observations match what we expect from studies of dark matter. Now, while both dark matter and normal matter are types of matter, they behave very differently. Early in the universe, normal matter had an electric charge and interacted strongly with light, which caused it to scatter. Dark matter, on the other hand, doesn't interact directly with light, but it still affects the universe in other ways. For example, it influences the cosmic microwave background, CMB, through its gravitational pull, especially on large scales. It also affects the movement and thickness of normal matter. Because of these differences, normal matter and dark matter evolve in separate ways and leave clear marks on the CMB. The CMB is very close to being a perfect blackbody, meaning it gives off a smooth, even temperature. However, there are tiny temperature differences, about 1 part in 100,000, that scientists can study. These small variations, called anisotropies, can be mapped across the sky. When scientists turn this map into a graph called the angular power spectrum, they see a series of peaks that are evenly spaced but have different heights. The exact positions of these peaks depend on key factors in cosmology, and by comparing these positions to scientific models, we can learn more about what the universe is made of. The first discovery of the CMB's anisotropies happened in 1992 by the COBE satellite, but the resolution wasn't high enough to see the detailed peaks. In 2000, the Boomerang experiment, using a balloon to take measurements, found the first of these peaks. Later, the WMAP satellite and the Planck spacecraft measured these peaks much more accurately. Their results supported the Lambda CDM model of cosmology. The process of forming structures began shortly after the Big Bang, when small differences in the universe's density caused matter to gather and form stars, galaxies, and groups of galaxies. Before this time, the universe was smooth, with no major differences in density, as explained by the Friedmann solutions to general relativity. Over time, tiny changes in density started to grow and pull together, turning the simple, featureless universe into a more complex structure filled with stars and galaxies. In the early stages, radiation controlled the universe and had a big effect on matter. This radiation stopped normal matter's density changes from growing and forming structures. If the universe only had normal matter, these changes would not have had enough time to turn into the galaxies and groups of galaxies we see today. The key to solving this problem lies in dark matter, which is not affected by radiation. This allowed its density changes to grow first, creating gravitational pull that later helped normal matter collapse into galaxies and other structures. The gravity from dark matter acted like a magnet, pulling in normal matter and speeding up the formation of these huge cosmic structures. A clear example of the impact of dark matter is the bullet cluster, formed by the collision of two large galaxy clusters. What makes the bullet cluster especially interesting is the difference between where the mass of the cluster is located according to gravitational lensing, the bending of light around large objects, and where the visible matter is found. This difference is difficult to explain with other gravity theories, which expect gravitational lensing to happen only around visible matter. However, the regular theory of dark matter can easily explain this. The visible gas in the clusters, which interacts with light and other forms of radiation, was slowed down and cooled by electromagnetic forces during the collision. Dark matter, on the other hand, doesn't interact with light in the same way, so it passes through the collision unaffected, separating from the visible gas. This created two separate lensing peaks as seen. In addition to dark matter, astronomers use Type Ia supernovae as standard candles to measure distances across the universe. These supernovae have a known brightness, so by measuring how dim they appear, scientists can figure out how far away they are. This method has shown that the universe is expanding faster and faster, a phenomenon usually connected to dark energy. Baryon acoustic oscillations, BAO, refer to regular changes in the density of normal matter, baryons, in the universe, which happened on large scales in the early universe. These changes were caused by sound waves traveling through the hot, dense fluid of photons and baryons before the universe cooled enough for atoms to form. The effects of these sound waves can still be seen in the cosmic microwave background, CMB, radiation. As the universe expanded, dark matter and normal matter began to group together, but the effect of the original changes weakened over time. However, we can still see a slight tendency for galaxies to be separated by about 147 million light-years, which is a subtle but measurable sign of these early changes. This pattern was predicted in the 1990s and confirmed in 2005 through large galaxy surveys like the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey. By combining CMB observations with BAO measurements, scientists can get an accurate estimate of important cosmic values, such as the rate of expansion of the universe and the amount of matter it contains. These results support the lambda CDM model, which is the current leading theory of cosmology. Large surveys of galaxy redshifts can help us create a three-dimensional map of how galaxies are spread out in the universe. However, these maps are not perfect because the distances we estimate are based on the redshift we observe. The redshift we measure is affected by two things. The main factor is the universe's expansion, but there's also a smaller influence from the galaxy's own motion, known as its peculiar velocity. In general, superclusters, groups of many galaxies, are growing more slowly than the average expansion of the universe because their gravity is pulling things together. On the other hand, voids, vast empty spaces between galaxies, are expanding faster than the universe as a whole. This difference in expansion causes some interesting effects. For example, galaxies that are located in front of a supercluster are moving toward it faster than expected, so their redshift will be a little higher than we would normally calculate for their distance. Conversely, galaxies behind the supercluster appear to have a slightly lower redshift than expected. This difference causes superclusters to look flattened along the line of sight, while voids look stretched. However, this effect is hard to notice in a single structure, since we don't know its exact shape. Instead, scientists can observe this effect by averaging data from many structures. The phenomenon was first predicted by Nick Kaiser in 1987 and was later confirmed in 2001 by the 2DF Galaxy Redshift Survey, with results matching what we expect from the lambda CDM model of the universe. In a related field of study, the Lyman alpha forest refers to the collection of absorption lines found in the spectra of distant galaxies and quasars. These lines are caused by neutral hydrogen absorbing light at a specific wavelength, called the Lyman alpha transition. Observations of the Lyman Alpha forest help astronomers test and refine cosmological models, with results that align with findings from the WMAP data. Dark matter is often grouped into three types: cold, warm, and hot. These labels don't refer to temperature, but instead describe the speed at which the particles were moving in the early universe. In simple terms, they indicate how far the particles traveled due to random motions before the universe began expanding and slowed them down. This distance is known as the free streaming length, FSL. The classification of dark matter depends on how this FSL compares to the size of a protogalaxy, an early cosmic object that would eventually turn into a small galaxy. If the FSL is much smaller than the size of a protogalaxy, it's considered cold dark matter. If it's about the same size, it's warm dark matter. And if the FSL is much larger, it's hot dark matter. There are also theories that suggest a mix of these types, which were more popular in the mid-1990s, but became less favored after the discovery of dark energy. The key idea behind the free streaming length is that, after the Big Bang, the universe began with small fluctuations in density, which were caused by tiny quantum variations at the smallest scales. As these particles moved from denser areas to less dense ones, the rapid expansion of the universe put a limit on how far they could travel. Faster particles, like those in hot dark matter, could travel further before the universe expanded too much, while slower particles, such as those in cold dark matter, couldn't move as far. This means that the free streaming length sets a limit on the size of structures that could form in the early universe. Hot dark matter would lead to the formation of large structures, like superclusters, which would eventually break apart into galaxies. In contrast, cold dark matter allows for smaller structures like galaxies to form first. Recent observations, especially deep-field images of the universe, show that galaxies were the first to form, followed by groups of galaxies and large groups of galaxies as they join together. This supports the idea that most dark matter is cold, not hot. This is also why neutrinos, which move almost at the speed of light and would be considered hot dark matter, cannot explain most dark matter. Dark matter refers to any type of matter that interacts with visible matter, like stars and planets, mainly through gravity. This means that dark matter might not be made of a completely new type of particle, but could, in theory, include regular matter like protons or neutrons. In fact, many objects familiar to astronomers, such as planets, brown dwarfs, red dwarfs, stars, white dwarfs, neutron stars, and black holes, belong to this category. For example, when a black hole pulls in matter, it doesn't differentiate between regular matter, like protons, and other kinds of matter. Once it's inside the event horizon, all matter is treated the same. These hard-to-detect objects are grouped together as machos, massive compact halo objects. Some scientists once thought that machos made up most of dark matter, but this idea has since been mostly rejected. There is strong evidence suggesting that most of dark matter is not made up of regular visible matter. First, if there were enough regular matter like gas or dust scattered around, we would be able to see it when it's lit up by the light from stars. However, we don't see this kind of matter in the amounts we would expect. Next, the Big Bang theory helps us understand how the elements we see today were created. According to this theory, if there were more normal matter, called baryons, in the early universe, we would have seen a higher abundance of elements like helium, lithium, and other heavier elements. Based on what we observe, we know that only about 4 to 5% of the universe's total mass consists of this regular matter. However, large-scale studies of galaxies and other cosmic structures show that the total amount of matter is about 30% of what is needed to keep the universe stable. Further studies have shown that only a small portion of dark matter seems to be in the form of regular hidden objects, like small planets or black holes called machos. Studies involving the bending of light by gravity, gravitational microlensing, suggest that these objects can't explain most dark matter, as their masses fall within a range that excludes nearly all of the plausible candidates. Detailed studies of the cosmic microwave background, the faint radiation left over from the Big Bang, by missions like WMAP and Planck, provide strong evidence that about 5/6 of the matter in the universe doesn't interact much with light or regular matter, except through gravity. This suggests that dark matter is mostly invisible and can only be detected through its gravitational influence. If regular matter, called baryonic matter, doesn't explain most of dark matter, then dark matter must be made of something else, specifically non-baryonic matter. There are two main possibilities for non-baryonic dark matter: new mysterious particles and ancient black holes from the early universe. Unlike baryonic matter, these non-baryonic particles don't help create the elements that formed during the Big Bang, a process known as Big Bang nucleosynthesis. Instead, we only notice them because of the gravitational effects they create, such as how they bend light, called weak lensing. Some types of dark matter can even interact with each other, self-interacting dark matter, or with regular particles like WIMPs, weakly interacting massive particles. These interactions might produce detectable signs, such as gamma rays and neutrinos, which scientists could potentially observe, indirect detection. There are many different candidates for dark matter, each with strengths and weaknesses. WIMPs don't have a strict definition, but they are generally thought of as elementary particles that interact through gravity and possibly other weak forces, such as the weak nuclear force. Many theories suggest that WIMPs were created in the early universe in a similar way to regular particles. These particles would make up what's called cold dark matter. To explain how much dark matter we have today, the WIMP particles would need to be able to annihilate with each other in a specific way, which matches what would happen if they had masses around 100 giga-electron volts and interacted through the electroweak force. This idea is often referred to as the WIMP miracle because it fits so well with predictions from supersymmetric theories, which extend the standard model of particle physics. A stable partner particle from supersymmetry has long been seen as a prime candidate for dark matter. Researchers are working hard to find WIMPs by looking for the products of their annihilations, such as gamma rays, neutrinos, and cosmic rays coming from nearby galaxies. They also use experiments designed to directly detect WIMPs in laboratories by measuring their interactions with atomic nuclei, or by trying to create WIMPs in particle colliders like the Large Hadron Collider, LHC. However, in the early 2010s, experiments didn't find strong evidence for supersymmetry, and the LHC results cast doubt on the simplest WIMP ideas. Axions, another candidate for dark matter, are theoretical particles that were first proposed in 1978 by Frank Wilczek and Steven Weinberg. These particles were originally suggested to solve a problem in the theory of quantum chromodynamics, QCD, which explains how quarks and gluons interact. Axions are incredibly light and weakly interact with other particles, making them a perfect candidate for dark matter. They could be produced in the early universe and would remain present today, their abundance depending on their mass. Axions are thought to be so light that they could help explain some of the small-scale issues in the lambda CDM model, the leading cosmological model. The axion theory has gained popularity in recent years, especially after WIMPs were not detected. The axion's extremely low mass means that quantum effects could potentially explain the small-scale mysteries of dark matter. Primordial black holes, another interesting idea, are believed to have formed in the very early universe, right after the Big Bang. During the period of rapid growth known as inflation, incredibly dense regions of tiny matter could have collapsed under their own gravity, creating black holes without needing a star's death, as is the case with regular black holes. These black holes would have existed before the first stars and could have masses ranging from tiny, even as small as atoms, to incredibly large, much bigger than usual stellar black holes. The idea of primordial black holes was first suggested in 1967 by Yakov Zeldovich and Igor Novikov, and later by Stephen Hawking in 1971. The idea quickly became popular as a possible explanation for dark matter. One of the benefits of primordial black holes as dark matter candidates is that the theory behind black holes is already well known in physics, general relativity, and black holes themselves are already confirmed to exist. However, creating primordial black holes might require special conditions, such as unusual cosmic inflation, or ideas beyond the standard model of particle physics. In 2015, gravitational wave measurements from the detection of black hole mergers sparked renewed interest in primordial black holes as dark matter. Some black holes detected by these experiments had masses that seemed too large to be formed by the usual processes, like the collapse of a star. This suggested they could be primordial. However, a study that looked for signs of gravitational lensing from medium-sized black holes, expected to be dark matter, found no evidence for them, although some researchers think this could be due to assumptions about the mass of these black holes. Further observations, like those made by the James Webb Space Telescope, may provide more clarity on this theory. Scientists once thought that incredibly small black holes, known as primordial black holes, might make up a large part of dark matter. However, the Voyager 1 spacecraft, which explored beyond the Sun's reach, measured the flow of positrons and electrons and found something surprising. The number of particles detected was too low, and their energy levels were not what scientists expected. This led researchers to conclude that these tiny black holes are too rare to account for dark matter. Despite this, the idea of dense forms of dark matter continues to be researched, with new theories even suggesting ways to cool dark matter. As of 2018, the mystery remains unsolved. In 2019, further observations of the Andromeda Galaxy showed no signs of microlensing effects, which would be expected if tiny black holes were present, adding more doubt to their existence. However, there's still a gap in our understanding. There is a range of mass smaller than what we can currently detect with optical microlensing, where primordial black holes could potentially make up all of the dark matter. This area remains open for exploration and continues to challenge our understanding of the universe. If dark matter is made of particles that barely interact with anything, an important question arises. Could these particles form objects like planets, stars, or black holes? Historically, the answer has been no, and there are two key reasons for this. It can't easily lose energy. Regular matter forms dense objects like stars and planets because it can lose energy in many ways. For example, when particles fall inward due to gravity, they can lose energy, which allows them to slow down and condense into more stable objects. Dark matter, however, doesn't seem to have the ability to lose energy because it doesn't interact with other matter strongly, except through gravity. Without ways to release energy, dark matter particles that start to get pulled inward would just heat up, speed up, and eventually escape, preventing the formation of compact objects. It doesn't interact in many ways. Regular matter interacts through multiple forces, such as gravity, electromagnetism, and the strong nuclear force, allowing it to form complex structures like atoms, stars, and galaxies. For instance, inside stars, particles interact through nuclear fusion, emitting light and neutrinos. In dark matter, we don't see evidence for such interactions beyond gravity, and possibly some weak interactions, but this is still speculation. Without these varied interactions, dark matter doesn't have the ability to form the kinds of structures that regular matter does. If dark matter is composed of tiny particles, these particles pass through every square centimeter of Earth, millions or even billions of times every second. Many experiments are trying to test this idea. While WIMPs, weakly interacting massive particles, have been the most commonly searched for candidates, axions are also getting attention, especially with projects like the Axion Dark Matter Experiment, ADMX. Other possibilities include heavy particles from a hidden sector that only interact with regular matter through gravity. There are two main types of experiments investigating dark matter: direct detection experiments. These look for signs that dark matter particles are scattering off atomic nuclei in a detector. The goal is to measure tiny energy shifts, a few keVs, caused by these interactions. When dark matter hits an atom, the atom might release energy in the form of light or vibrations, which can be detected. To do this well, these experiments need to be as isolated as possible from background interference, which is why they are often conducted deep underground, where cosmic rays don't interfere. Notable underground labs include Stowell Mine, Sudan Mine, and the Gran Sasso National Laboratory. These experiments often use two technologies: cryogenic detectors that measure heat from particle collisions in materials like germanium, noble liquid detectors that detect light produced when a particle hits liquids like xenon or argon. Some prominent experiments in these areas include CDMs, CREST, xenon, and LUX. These detectors are particularly good at distinguishing dark matter from background particles, which mostly scatter off electrons, while dark matter particles scatter off atomic nuclei. Indirect detection experiments. These look for the after effects of dark matter particles annihilating or decaying. There's currently no confirmed detection of dark matter in direct detection experiments, but these efforts have helped narrow down the possible properties of dark matter particles. One interesting claim comes from the Dharma Nyai and Dharma Libra teams, which have noticed a yearly change in their data, possibly because the Earth is moving through the dark matter field. However, other experiments such as LAX and Super CDMS have not observed the same effect, creating some confusion. There are also special experiments with directional sensitivity, which track the motion of dark matter particles based on the solar system's movement around the center of the galaxy. This method tries to separate dark matter signals from background noise, which should be spread out evenly. These experiments, such as DMT-PC and drift, try to detect the direction in which dark matter is moving to help identify potential signals. Indirect detection experiments aim to find signs of dark matter by looking for the results that appear when dark matter particles break apart or decay in space. In certain areas with a lot of dark matter, like the center of the Milky Way, two dark matter particles might collide and destroy each other, releasing gamma rays or pairs of regular particles and their opposites, antiparticles. Alternatively, if a dark matter particle is unstable, it might break down into regular particles or others, which could be detected indirectly through an unexpected increase of gamma rays, antiprotons or positrons coming from areas with a lot of dark matter like the Milky Way's center or faraway galaxies. One of the challenges of this type of search is that other cosmic events could produce similar signals, so multiple signals from different sources are needed to confirm a dark matter discovery. Dark matter particles that pass through the Sun or Earth might interact with atoms and lose energy in the process. This could cause dark matter to build up at the centers of these celestial bodies, increasing the chances for collisions or destruction. These events could send out a unique signal of high-energy neutrinos, which could serve as strong proof of dark matter made of WIMPs, weakly interacting massive particles. Instruments like Amanda, IceCube, and Antares are actively searching for this signal. In addition, the detection of gravitational waves by LIGO in 2015 opened the door for observing dark matter in new ways, especially if it exists as ancient black holes. Several experiments have tried to detect dark matter emissions, such as those from destruction or decay. For example, the Energetic Gamma Ray Experiment telescope spotted more gamma rays in 2008 than expected from the Milky Way, but scientists believed this was due to errors in estimating the telescope's sensitivity. The Fermi Gamma Ray Space Telescope is continuing this search, and in 2009, it observed a puzzling extra amount of gamma rays from the center of the Milky Way. This could be a sign of dark matter destruction or an unknown group of pulsars. In 2012, a deeper look at Fermi data suggested a 130 giga-electron volts signal from the Milky Way's center, which was thought to be a possible result of WIMP destruction. At even higher energies, ground-based telescopes have set limits on dark matter destruction in small galaxies and galaxy clusters. The Pamela experiment, launched in 2006, detected an unusual amount of positrons, which might come from dark matter or pulsars, though no similar extra amount of antiprotons was found. Similarly, the Alpha Magnetic Spectrometer aboard the International Space Station observed high-energy cosmic rays in 2013, possibly linked to dark matter destruction. Another approach to finding dark matter involves trying to create it in a laboratory. Experiments like those at the Large Hadron Collider, LHC, may detect dark matter particles formed during proton collisions. Since dark matter doesn't interact much with regular matter, it might be spotted indirectly by noticing large amounts of missing energy and momentum that escape detection, while other particles from the collision are measured. The LEP experiment, using a similar method but probing the interaction between dark matter and electrons, also provides limits on dark matter. Any discovery of dark matter in such experiments must be verified by findings from indirect or direct detection methods to confirm that the new particle is truly dark matter. Since dark matter has yet to be identified, many other theories have emerged to explain the same cosmic events. General relativity, the theory that supports much of the evidence for dark matter, is well tested on the scale of the solar system, but hasn't been fully proven on galactic or cosmic scales. Some scientists propose that changing general relativity could remove the need for dark matter. Well-known alternatives include MOND, modified Newtonian dynamics, TVES, a relativistic version of MOND, FR, gravity, negative mass, dark fluid, and entropic gravity, among others. A key challenge for these alternative theories is that the evidence for dark matter comes from many independent sources. While it might be possible to explain a single observation, explaining all the evidence without dark matter is very difficult. Still, some alternatives have had limited success, like the 2016 test of gravitational lensing in entropic gravity and a 2020 measurement supporting MOND. Despite these successes, most astrophysicists believe that while changes to general relativity could explain some of the observations, the overall data suggests that dark matter must exist in some form. Another cosmic mystery is dark energy. In the study of the universe, dark energy is a strange type of energy that affects the universe on the biggest scales. Its main job is to speed up the universe's expansion. If the current model of the universe is right, dark energy makes up 68% of all the energy in the universe today. By comparison, dark matter makes up 26%, and normal matter is only 5%. Other types of energy, like neutrinos and light particles, add up to almost nothing. Even though dark energy has a very low density, about 7 in 10 billion grams per cubic centimeter, which is much smaller than regular or dark matter, it still controls the universe's energy balance because it spreads evenly through space. Scientists first started to suspect dark energy existed after studying light from faraway exploding stars called supernovae. A special type called Type Ia supernovae is very useful for measuring distances because they always shine with the same brightness. By comparing their light to their redshift, which shows how fast they are moving away, scientists found out that the universe is expanding faster and faster instead of slowing down as they had once believed. Before this, most thought that the pull of gravity from all the matter and energy in the universe would gradually slow the expansion. Since this surprising discovery, many different pieces of evidence have confirmed that dark energy is real. Even though scientists have detected dark energy, they still don't fully understand what it is. Several ideas try to explain it. One idea is the cosmological constant, which means dark energy is a steady, unchanging force spread evenly across space. Another idea is scalar fields, which are energy sources that change over time and in different places, like quintessence or moduli. If the cosmological constant is correct, dark energy stays the same everywhere and at all times. But if scalar fields exist, dark energy could vary. Other ideas include interacting dark energy, which suggests that dark energy could be affected by other forces, and cosmological coupling, which suggests dark energy might interact with gravity in ways we don't yet understand. The cosmological constant is a term that can be added to Einstein's equations in general relativity. When seen as a source term in these equations, it can be thought of as the energy of empty space, also called vacuum energy. This energy could be positive or negative, depending on how it is understood. Einstein first introduced the cosmological constant to make his equations describe a still, unchanging universe. He thought this constant would act as a force that cancels out gravity's pull, using a kind of dark energy to keep everything from collapsing. He used the symbol capital lambda to represent this idea. Einstein described it as empty space, behaving like negative mass, spreading through the vast universe and helping to stop collapse. However, scientists soon found out that this idea wasn't stable. Even a tiny change in the universe's size would cause it to either grow uncontrollably or shrink forever. In Einstein's model, the universe wasn't truly balanced. If the universe grew even a little, it would create more vacuum energy, making expansion speed up. If the universe shrank, it would keep collapsing. Einstein also suggested that empty space could have its own energy that would not weaken as space itself expanded. As space got bigger, this energy would also increase, causing the universe to expand faster. This type of expansion is bound to happen because matter in the universe is not spread out evenly. In 1929, Edwin Hubble's observations showed that the universe wasn't still, it was actually expanding. This discovery made Einstein call his earlier idea of a still universe his biggest mistake. In 1980, Alan Guth and Alexei Starobinsky proposed a theory about the early universe called cosmic inflation. They suggested that a force, similar to dark energy, caused a sudden and extremely fast expansion right after the Big Bang. This quick expansion, known as inflation, is a key part of today's theories about the beginning of the universe. However, the energy needed for inflation was much higher than the dark energy we see now. The exact link between dark energy and inflation is still a mystery, but after inflationary theories became widely accepted, the cosmological constant seemed less important. During the 1980s, most scientists focused on models of the universe that contained mostly cold dark matter, CDM, and a small amount of normal matter. These models matched many observations of how galaxies formed, but they didn't explain everything. For example, they predicted a lower value for the Hubble constant than what was actually measured. They also had trouble explaining large groups of galaxies. These problems became even clearer after the 1992 discovery of small variations in the cosmic microwave background by the COBE spacecraft. New models were created, including the Lambda CDM model, which includes the cosmological constant. In 1998, studies of faraway supernovae confirmed that the universe's expansion was getting faster, providing the first strong proof of dark energy. Soon after, more observations supported the idea of dark energy. In 2000, the Boomerang and Maxima experiments studied the cosmic microwave background and found that the total energy of the universe was very close to the critical density. In 2001, the 2DF Galaxy Redshift survey showed that matter made up about 30% of this critical density. The missing part was explained by dark energy. More precise data from the WMAP satellite, gathered between 2003 and 2010, continued to support the Lambda CDM model, giving scientists a clearer picture of what the universe is made of. The term dark energy was first used in 1998 by Michael S. Turner, following the earlier concept of dark matter introduced by Fritz Zwicky in the 1930s. To truly understand how the universe grows over time and space, we need to make very accurate measurements of its growth. In the field of general relativity, we figure out how fast the universe is expanding by studying its shape and a key rule known as the cosmological equation of state. This rule explains how temperature, pressure, and the combined amounts of matter, energy, and vacuum energy are related in any part of space. One of the main goals in modern cosmology is measuring the equation of state for dark energy, which is one of the hardest challenges in the field today. When scientists add the cosmological constant to the standard model of cosmology, the FLRW metric, they create the Lambda CDM model. This model is often called the standard model of cosmology because it closely matches what we see in the universe. Since 2013, the Lambda CDM model has been confirmed by more and more accurate studies of the universe, including data from the Planck spacecraft and the Supernova Legacy Survey. Early results from the Supernova Legacy Survey show that dark energy's behavior, on average, closely matches the predictions of Einstein's cosmological constant, with an accuracy of about 10%. Recent findings from the Hubble Space Telescope's Higher Z team suggest that dark energy has been around for at least 9 billion years, even before the universe started expanding faster. Despite these studies, the true nature of dark energy is still unknown and remains a topic of much debate. Dark energy is believed to be very smooth and spread evenly across space, with little thickness, and it doesn't seem to interact with any of the known forces except gravity. Its extremely tiny weight, about 10 to the power of negative 27 kilograms per cubic meter, means it's unlikely to be detected in lab tests. Even though it is so thin and light, dark energy makes up about 68% of the universe's total energy. This is because it is thought to fill all empty space evenly, playing a huge role in how the universe expands. One major idea connects dark energy to vacuum energy. Vacuum energy refers to the tiny particles and antiparticles that are constantly appearing and disappearing in empty space, as described by Heisenberg's uncertainty principle. This ongoing change in energy is often considered a key cause of dark energy. According to Einstein's theory of relativity, this vacuum energy should have effects due to gravity. That means it adds to the cosmological constant, which in turn helps speed up the universe's growth. However, there's a big problem. The estimated value of vacuum energy based on quantum field theory is much higher than what is actually observed, and scientists are still struggling to solve this mismatch. No matter what dark energy really is, it must have a very strong negative pressure to explain why the universe is expanding faster. In general relativity, pressure acts like mass when it comes to its effect on gravity. Both pressure and mass are part of the stress-energy tensor, which is the key factor that determines how matter affects gravity. When applied to the universe's expansion, this negative pressure causes the universe to expand even faster. If the universe were shrinking, this pressure would actually slow down its collapse. This faster growth is sometimes called gravitational repulsion because it seems to push the universe apart, working against gravitational pull. Based on what we currently know about the universe, there are three main things that make up everything: matter, radiation, and dark energy. Matter is anything that has mass or takes up space, and it behaves in such a way that as the universe expands, its energy becomes less dense at a rate linked to the cube of the expansion factor. To make it simpler, imagine a box with ordinary particles inside. If the box doubles in size, the energy of those particles decreases by 8 times because they are spread over a bigger space. This happens because the box is growing in 3 directions, so the energy becomes more spread out. Radiation, such as light or heat, behaves a bit differently. Its energy becomes less dense even faster than matter as space grows. This happens because not only is the energy spread over a bigger area, but the light or radiation also gets stretched in wavelength as the universe expands. This stretching, called redshift, causes radiation to lose energy even faster than matter does. Then there is dark energy. Unlike matter and radiation, dark energy doesn't change based on how much space there is. It is a built-in part of space itself. No matter how much the universe expands, dark energy stays the same. Its energy remains constant. Unlike matter, which gets thinner as space grows, dark energy does not weaken. It is a strange force that keeps the universe's expansion speeding up. The proof for dark energy, even though it is indirect, comes from many different sources that work together to give us a clearer idea. Distance and redshift measurements. By studying how far objects are and how much their light is stretched, redshift, as the universe expands, scientists have found that the universe has grown more in its later stages than in its earlier ones. This suggests something is driving this faster expansion, which could be dark energy. Theoretical need for extra energy. The universe's flatness, meaning it doesn't seem to curve in any noticeable way, requires some kind of energy that isn't regular matter or dark matter. Scientists believe this energy is dark energy, which helps explain why the universe looks as flat as it does. Cosmic density waves. By studying large-scale patterns of mass in the universe, scientists have noticed clues that point to dark energy. These patterns, such as the way galaxies are arranged, provide more information about the universe's growth and its mysterious force. In 1998, a group of astronomers called the High-Z Supernova Search Team studied Type Ia supernova, exploding stars, and found something unexpected. The universe's growth was speeding up, not slowing down. Another group, the Supernova Cosmology Project, made similar discoveries in 1999. For their work, the scientists were awarded the Nobel Prize in Physics in 2011. Since then, many different observations have supported these results. Information from the cosmic microwave background, radiation left over from the Big Bang, the bending of light from galaxies, called gravitational lensing, and the structure of the universe all match the idea of dark energy, as predicted by the Lambda CDM model, a model of the universe. Some critics argue that only redshift and distance measurements give strong proof, but other findings like cosmic microwave background patterns also suggest distances larger than expected in a universe without dark energy. Supernovae are important tools for studying the universe because they act like standard candles. Their known brightness helps astronomers measure their distance, making it possible to track how the universe is expanding. By comparing how far away a supernova is and how much its light has shifted, redshift, scientists can estimate how fast the universe is growing. Type Ia supernovae are especially useful because they have a steady and predictable brightness, making them some of the most dependable markers in space. Recent information suggests that dark energy makes up about 71% of the universe, with dark matter and normal matter making up the rest. The theory that explains how galaxies, stars, and other objects form and grow also supports the idea that matter only makes up 30% of the universe's critical density. the amount needed to make the universe flat. In 2011, the Wiggle-Z Galaxy Survey, which studied over 200,000 galaxies, added more proof to the dark energy idea. Using a smart method, they measured the distances to galaxies up to 2 billion parsecs away. This helped confirm that the universe has been expanding faster over time, giving more support to the idea of cosmic acceleration. For the universe to be flat, as observed, there must be an extra form of energy, since the total amount of visible matter, both normal and dark, only makes up 30% of what's needed. The rest, about 70%, must be something like dark energy. Information from the Wilkinson Microwave Anisotropy Probe, WMAP, found that about 73% of the universe consists of dark energy, with the rest being dark matter and normal matter. More recent findings from the Planck spacecraft changed this to 68% dark energy, 27% dark matter, and 5% normal matter. Dark energy also explains certain patterns seen in the cosmic microwave background. When photons, light particles, pass through areas of strong gravity, like galaxy clusters or empty spaces between them, they lose energy, creating cooler and warmer spots in the background radiation. This effect, called the integrated Sachs-Wolf ISW effect, is another key clue pointing to dark energy. A newer way to measure dark energy involves using the Hubble constant, which tracks how the universe expands over time by studying galaxies that have passively evolved. These galaxies act as cosmic clocks, and by measuring their age and redshift, scientists can directly estimate how fast the universe has been expanding at different points in history. Dark energy remains one of the biggest mysteries in modern physics. Scientists believe it is a force that pushes the universe to expand, but they don't know exactly what it is or how it works. Because of this, researchers are looking at the problem from many angles. Some are re-examining Einstein's theory of gravity, some are trying to figure out the exact properties of dark energy, and others are searching for alternative explanations based on what they observe in the universe. One of the simplest ideas about dark energy is that it is a basic feature of space itself. In this view, empty space isn't really empty. It contains energy, often called vacuum energy. This idea is known as the cosmological constant, represented by the Greek letter lambda. It is the foundation of the widely accepted lambda-CDM model of the universe. Since energy and mass are connected by Einstein's equation, this vacuum energy should have a gravitational effect, shaping how the universe expands. However, there is a huge problem. Quantum physics predicts that the amount of vacuum energy should be much greater, about 120 times larger than expected. If this prediction were correct, the universe would have expanded so fast that galaxies, stars, and planets could never have formed. For the universe to exist as we see it today, something must be cancelling out most of this energy, but not completely. Scientists don't yet understand why this happens. Some physicists think that dark energy might not be a fixed force at all, but rather a changing energy field. This idea is called quintessence. Unlike the cosmological constant, which stays the same everywhere, quintessence can change across space and time. It acts like a field that fills the universe, influencing its expansion in a more flexible way. For quintessence to work, the energy field must be extremely light so that it doesn't clump together like normal matter. Some versions of this idea predict that the universe's expansion should be slightly slower than what the cosmological constant model suggests. However, no solid proof has been found yet to confirm or disprove quintessence. One of the most perplexing questions in modern cosmology is why dark energy emerged as the dominant force at precisely this moment in the universe's history. If the cosmic expansion had accelerated too soon, galaxies may never have had the chance to form, and life, at least as we understand it, might never have existed. Some scientists suggest that this is merely a cosmic coincidence, while others believe it could be evidence for the anthropic principle, which proposes that the universe must be the way it is because we are here to observe it. However, certain quintessence models introduce an elegant explanation, incorporating a tracker mechanism that naturally synchronizes dark energy's dominance with the density of radiation in the early universe. More extreme versions of quintessence introduce even stranger possibilities, pushing the boundaries of our understanding of cosmic evolution. One particularly unsettling variation known as phantom energy suggests that dark energy may not simply remain constant, but could actually increase in strength over time. If this scenario is correct, the universe's expansion would not just continue, it would accelerate uncontrollably until everything was torn apart in a catastrophic event known as the Big Rip. This apocalyptic fate would unfold in a chilling sequence. First, galaxies would be ripped from one another. Then individual solar systems would unravel as planets drifted away from their stars. Eventually, the very fabric of matter itself would come undone, with atoms shredded into their fundamental components as the force of expansion reached infinity. Another exotic hypothesis, known as K-essence, explores unusual forms of energy that defy conventional physics. Some versions of K-essence introduce negative kinetic energy, a bizarre concept that could have unforeseen and possibly chaotic consequences for cosmic evolution. Unlike phantom energy, which steadily grows in strength, K-essence could exhibit unpredictable fluctuations, potentially altering the universe's fate in ways we have yet to understand. Recent advancements in observational cosmology have introduced new puzzles, particularly in the form of discrepancies in the measurements of the universe's expansion rate, a problem referred to as the Hubble tension. Some researchers speculate that this inconsistency could indicate that only certain quintessence models, those incorporating additional forces or interactions, are viable. If so, dark energy may not be as simple as previously thought, and its true nature may be even more complex than Einstein's equations suggest. Despite its enigmatic nature, our understanding of dark energy is deeply intertwined with Einstein's theory of general relativity. Some scientists have proposed that if general relativity were modified in specific ways, we might not need dark energy at all to explain the universe's accelerated expansion. However, while alternative theories often generate excitement, they have struggled to match observational data with the same precision as the standard dark energy model. In fact, a pivotal breakthrough, the detection of gravitational waves from the event GW170817, has already ruled out many modified gravity theories. Astrophysicist Ethan Siegel points out that while alternative ideas make for fascinating discussion, the overwhelming consensus among experts is that dark energy is real. So far, no competing hypothesis has provided a more accurate description of the data. According to cosmological estimates, the universe's expansion began to accelerate approximately 5 billion years ago. Before that, the combined gravitational pull of dark matter and regular matter acted as a cosmic brake, slowing the expansion down. However, as the universe continued to grow, dark matter became more diluted, reducing its influence. Dark energy, on the other hand, remained nearly constant. Eventually, dark energy's repulsive force overtook gravity's pull, shifting the universe into a phase of unstoppable acceleration. For every time the universe doubles in size, the density of dark matter per unit of space is halved, whereas dark energy remains nearly unchanged. The ultimate fate of the universe depends entirely on the true nature of dark energy. If it remains constant, as proposed in the cosmological constant model, the universe will continue expanding indefinitely. Galaxies outside our local group will recede at ever-increasing speeds, eventually surpassing the speed of light, not in violation of relativity, but because space itself is stretching. Some galaxies, even those already moving away faster than light, may still send signals that reach us, but over time, the relentless expansion will create a cosmic event horizon, a boundary beyond which no light, no matter how long we wait, will ever reach us. Current estimates place this event horizon at roughly 16 billion light-years away. Any event occurring within this distance may still send light that will reach us far into the future. However, anything happening beyond this limit will forever remain outside our observational reach. As galaxies approach this boundary, the light they emit will be stretched to increasingly longer wavelengths, eventually shifting beyond the visible spectrum and fading from view entirely. From our vantage point, the universe beyond our local group will dissolve into darkness, leaving behind only a handful of galaxies in an otherwise empty expanse. Over the course of trillions of years, our local group of galaxies will remain gravitationally bound, but the energy within it will eventually disperse into a state of maximum entropy, a bleak scenario known as heat death. In this final stage, all available energy will be evenly distributed, rendering any form of useful work impossible. This outcome resembles what was once predicted for a matter-dominated universe before the discovery of cosmic acceleration reshaped our understanding of the cosmos. However, there exist alternative and far more dramatic possibilities. One such scenario, driven by the concept of phantom energy, envisions a universe where dark energy intensifies to the point of overwhelming every fundamental force. In this terrifying future, the so-called Big Rip, even the most resilient structures, from galaxy clusters down to individual atoms, will be torn apart as dark energy's influence grows boundlessly. Conversely, some models suggest that dark energy might not be a permanent fixture of the universe but could evolve over time, potentially reversing its effects. In this case, cosmic acceleration might eventually give way to a new phase of contraction, leading to a catastrophic event known as the Big Crunch, in which the universe collapses back into a singularity. Even more intriguing is the possibility that dark energy operates cyclically, driving the cosmos through endless cycles of expansion and collapse, an eternal dance of creation and destruction, where each Big Bang is merely the beginning of a new cosmic epoch. Deep in the vastness of space, far beyond our solar system, lies an extraordinary planet, HD 189733b. At first glance, this alien world appears stunning, with a rich blue color reminiscent of Earth's oceans. But beneath its mesmerizing appearance hides one of the most violent and inhospitable environments known to science. This distant exoplanet, located about 63 light-years away, is anything but serene. It is a place where winds rage at unimaginable speeds, temperatures soar beyond 2,000 degrees Fahrenheit, and rain falls, not as water, but as razor-sharp shards of molten glass. The brilliant blue color of HD 189733b is not caused by vast bodies of water like those on Earth. Instead, it results from tiny particles of silicate floating in its thick atmosphere. These microscopic grains scatter light in a way similar to how Earth's sky appears blue during the day. However, this color is deceiving. Rather than signaling a calm and habitable environment, it masks an unimaginably harsh and chaotic world where storms rage endlessly. While storms on Earth can be fierce, nothing compares to the weather on HD 189733b. Winds on this planet reach astonishing speeds of over 2,000 miles per hour. To put this into perspective, the most powerful hurricanes and tornadoes on Earth typically produce winds of around 200 miles per hour at their peak. This means the winds on HD 189733b are 10 times stronger than the most violent storms we experience on Earth. These winds are not just fast, they are also dangerous. They carry enormous amounts of silicate dust and particles, creating an atmosphere filled with tiny, sharp grains of glass. The planet's close proximity to its host star results in extreme heating, which further fuels these raging storms. As the winds roar across the planet, they create a nightmarish landscape where survival would be impossible. The intense conditions on HD 189733b are largely due to its close orbit around its star. The planet is classified as a hot Jupiter, meaning it is a gas giant similar in size to Jupiter, but orbits its star at an extremely close distance. Because of this, the temperature on the planet's dayside can reach well over 2,000 degrees Fahrenheit. This is hotter than the surface of some stars and hot enough to melt many types of metal. Meanwhile, the night side of the planet, though cooler than the day side, still experiences intense and rapid temperature shifts. This drastic difference between the two sides creates extreme atmospheric movements, further driving the relentless winds and storms that dominate the planet. The rapid heating and cooling of the atmosphere help create one of the most terrifying weather systems in the known universe. One of the most mind-boggling features of HD 189733b is its rain. Unlike Earth, where rain is made of liquid water, the intense heat and atmospheric pressure on this planet cause something far more dangerous: glass rain. The silicate particles that float in the planet's atmosphere can exist in a gaseous state due to the extreme temperatures. However, when these particles move into cooler regions, they condense and form small, solid shards of silicate, essentially tiny pieces of glass. As the violent winds carry these glass particles through the atmosphere, they eventually fall back toward the planet's surface as a deadly high-speed rainstorm. Imagine standing in a storm where, instead of water droplets, sharp fragments of glass are hurled through the air at thousands of miles per hour. These shards, driven by hurricane-force winds, could slice through anything in their path, making the planet completely uninhabitable. No human, spacecraft, or piece of technology could survive such an environment. If a human were somehow able to visit HD 189733b without protective equipment, their experience would be short-lived and unimaginably painful. The brutal conditions of this world would mean instant death in multiple ways. The extreme heat of over 2,000 degrees Fahrenheit would cause immediate and severe burns, likely vaporizing any exposed tissue in moments. The relentless winds, moving at thousands of miles per hour, would tear apart anything caught in their grasp. The razor-sharp silicate shards falling from the sky would act like a deadly hailstorm, cutting deep into flesh and bone. Even a single shard traveling at such high speeds could be fatal. There is no material or protective suit known to humanity that could withstand the combined forces of intense heat, brutal winds, and high-speed glass rain found on this planet. The alien world of HD 189733b is one of the most extreme and hostile planets ever discovered. Imagine a place where survival is impossible, not just for humans, but even for most advanced technologies. The planet's environment is shaped by its blistering heat, ferocious winds, and an atmosphere filled with microscopic glass particles, elements that make it one of the deadliest exoplanets known to science. HD 189733b orbits extremely close to its star, absorbing an immense amount of energy. This results in daytime temperatures soaring to nearly 2,000 degrees Fahrenheit, hot enough to melt most metals. The extreme heat causes the air to expand violently, creating powerful atmospheric disturbances. Meanwhile, the night side, forever hidden from the star due to the planet's tidal locking, remains significantly cooler. This temperature contrast generates intense pressure differences, fueling hurricane-like winds that never stop. The winds on HD 189733b are not just strong, they are catastrophic. Blasting at speeds exceeding 2,000 miles per hour, they are nearly 3 times faster than the speed of sound. These winds can carry particles of silicate, essentially tiny shards of glass, turning the planet's weather into a deadly spectacle. If a human were somehow exposed to these conditions, the winds alone would be lethal, shredding any protective suit with razor-sharp grains of airborne glass. One of the most terrifying aspects of this planet is its glass rain. The atmosphere contains clouds rich in silicate particles. When these particles cool and condense, they form tiny glass-like droplets. But rather than falling gently, these droplets are hurled sideways at over 2,000 miles per hour by the violent winds, creating a relentless storm of cutting, high-speed glass. This phenomenon gives the planet its eerie, shimmering blue appearance, beautiful from afar, but a death trap up close. The extreme weather conditions of HD 189733b are caused by more than just heat and wind. The planet's atmosphere is constantly churning, with powerful storms forming and dissolving at breakneck speed. The interaction of intense heat, rapid rotation, and chemical reactions within the atmosphere creates an environment that is unpredictable and deadly. HD 189733b is an exoplanet unlike anything in our solar system. This massive world orbits its star at an incredibly close distance, exposing it to intense heat and radiation. Because of its extreme proximity, the planet absorbs a tremendous amount of energy from its star, which leads to an environment that is both violent and unforgiving. The surface of the planet is a battlefield of unrelenting forces, where extreme temperatures and ferocious winds dominate the landscape. One of the most striking features of HD 189733b is that it is tidally locked, meaning that one side of the planet is forever facing its star, while the other side remains in eternal darkness. This creates a severe imbalance between the day side and the night side. On the side that faces the star, temperatures soar to nearly 2,000 degrees Fahrenheit. In contrast, the night side is much cooler, though still far from what we would consider habitable. This dramatic temperature difference sets off a relentless cycle of chaotic weather patterns, making the planet one of the most hostile environments ever discovered. The day side of HD 189733b is essentially a scorching wasteland where the heat from the star fuels violent atmospheric activity. The gases in the atmosphere heat up rapidly, causing them to expand and generate massive pressure variations. This in turn leads to hurricane-like winds that roar across the planet's surface at unimaginable speeds, exceeding 2,000 miles per hour. These winds are far beyond anything ever recorded on Earth and are powerful enough to rip apart anything in their path. The weather on HD 189733b is not just extreme, it is utterly terrifying. Unlike the rain showers we experience on Earth, where water falls gently from the sky, this exoplanet experiences storms of liquid glass. The high temperatures and strong winds cause silicate particles in the atmosphere to condense into tiny shards of glass, which then fall from the sky as deadly precipitation. Imagine standing on the surface of this world during one of these storms. The sky would be an eerie, swirling mix of deep blues and shifting shadows, illuminated by the light of the planet's star filtering through thick, silicate-laden clouds. The atmosphere would be dense with heavy mist, refracting light in dazzling patterns. However, the beauty of the scene would be deceptive, as the glass rain would not simply drift down like snowflakes. It would plummet at speeds exceeding several hundred miles per hour. These razor-sharp fragments would slice through anything they encounter, making survival on this planet utterly impossible. The winds, which whip across the surface with hurricane-force intensity, would make the environment even more dangerous. Instead of merely falling to the ground, the glass shards would be caught in the air currents, turning the sky into a swirling vortex of deadly debris. The entire atmosphere would appear alive, a violent storm of silicate particles illuminated by the eerie glow of the planet's burning dayside. The sensation of standing in such a place would be overwhelming, as the sky itself would seem to be in constant motion, a relentless force of destruction and chaos. Despite the planet's extreme conditions, scientists have found ways to study HD 189733b using advanced astronomical techniques. Since this distant world is impossible to visit, researchers rely on powerful space telescopes to gather data. One of the primary methods used to analyze exoplanets like this one is spectroscopy, a technique that breaks down light into different wavelengths. By studying how light from the planet's star passes through its atmosphere, scientists can determine the chemical composition of its clouds and identify the presence of unusual substances, such as silicates that form the deadly glass rain. Space telescopes like the Hubble Space Telescope and the more advanced James Webb Space Telescope have been crucial in unlocking the secrets of this alien world. By carefully observing how the planet moves in front of its star, a process known as a transit, astronomers can analyze the changes in light to understand the properties of its atmosphere. This technique has revealed that HD 189733b has an atmosphere filled with silicate particles, providing the first evidence of glass rain in an exoplanetary system. In addition to direct observations, scientists use powerful computer models to simulate the extreme conditions of this world. These simulations allow researchers to predict weather patterns, wind speeds, and temperature variations, helping them to better understand how such an environment can exist. By feeding real observational data into these models, scientists can recreate the storms, heat distribution, and atmospheric composition of HD 189733b, gaining valuable insights into the dynamics of extreme planetary weather. The study of HD 189733b is not just about understanding one planet. It is about expanding our knowledge of the universe and the incredible diversity of worlds that exist beyond our solar system. This exoplanet serves as a prime example of how different planetary environments can be, showing us that the conditions on other worlds can be far more extreme than anything we could have imagined. The findings from HD 189733b also help scientists refine their search for potentially habitable planets. By studying the most hostile and uninhabitable places, researchers gain a better understanding of what makes a planet truly capable of supporting life. While HD 189733b itself is a nightmarish world of scorching heat, raging storms, and deadly glass rain, the techniques used to study it will one day help us find planets that could be more like Earth, places where life might actually thrive. In the grand scheme of the cosmos, HD 189733b is a testament to the raw power of nature. It is a world where the forces of heat, wind, and pressure collide in a never-ending battle, creating an environment that is both stunning and terrifying. The study of such extreme exoplanets not only fuels our curiosity, but also deepens our appreciation for the unique balance that makes Earth a rare and habitable gem in the vastness of space. HD 18973. 3b is a fascinating planet that helps scientists understand how massive gas giants, known as hot Jupiters, form and evolve. These planets are unique because they are not only enormous, but also orbit extremely close to their parent stars. Studying this planet has given researchers valuable clues about how such giants develop and change over time. One of the most important ideas linked to planets like this is the theory of planetary migration. This theory suggests that giant planets do not form close to their stars, but are instead born much farther away. Over time, gravitational forces push them inward until they settle in their current orbits. Observations of HD 189733b support this theory, as scientists have noted its rapid orbit and extreme atmospheric conditions. By analyzing these features, researchers can better understand how hot Jupiters interact with their surroundings. Because this planet is so close to its star, it experiences extreme heating. This intense heat plays a crucial role in shaping its atmosphere and weather. Scientists have discovered that its atmosphere contains fast-moving winds, unusual chemical reactions, and even rain made of tiny glass-like particles. These findings challenge previous models of how planetary atmospheres work, pushing scientists to rethink how elements and gases behave in high-temperature environments. By studying planets like HD 189733b, researchers can gain a deeper understanding of the forces that shape distant worlds and apply these insights to other exoplanets. The impossible challenge of building a base on HD 189733b. If humanity ever attempted to establish a base on this planet, it would face some of the most extreme and dangerous conditions imaginable. The biggest problem would be the planet's brutal weather. Winds on HD 18973. 3b reach speeds of more than 2,000 miles per hour. These winds carry tiny shards of silicate glass, which means that anything built on the planet's surface would need to be made of incredibly strong materials to withstand the constant bombardment. Another major challenge is the intense heat. Temperatures on this planet can reach nearly 2,000 degrees Fahrenheit, which is hot enough to melt many types of metals. Any human base would need to be equipped with advanced cooling systems and heat-resistant materials to prevent it from being destroyed. Radiation is another serious concern. Unlike Earth, HD 189733b does not have a protective magnetic field. Without one, the planet is exposed to deadly radiation from its parent star. Any human settlement would require thick shielding to protect astronauts from these harmful rays. Engineers would have to design underground or heavily reinforced structures to keep people safe from constant radiation exposure. On top of these dangers, simply getting people and supplies to such a distant world would be an enormous challenge. Since HD 189733b is located over 63 light-years away from Earth, sending equipment and resources there would take an incredibly long time. The only way for a base to survive would be if it could generate its own power, recycle its water, and even produce food on site. All these challenges make it clear that building a base on this planet would require technology far beyond what we currently have. While it might be possible one day, for now, HD 189733b remains one of the most extreme and inhospitable worlds ever discovered. However, by studying it, scientists continue to unlock the secrets of distant planets and the forces that shape our universe. In the vastness of space, there are planets that defy imagination, pushing the boundaries of what we know about the universe. One such planet is WASP-12b, an exoplanet that orbits so dangerously close to its parent star that it is literally being ripped apart. Scientists have been closely studying this planet, and what they have discovered is both astonishing and terrifying. WASP-12b is located approximately 1 million miles from its star. To put this into perspective, that is about 1/8 of the distance between Earth and the Sun. Because of this extreme proximity, the planet completes one full orbit in just one Earth day, meaning that a year on WASP-12b lasts only 24 hours. This rapid orbit results in a bizarre planetary environment. Unlike Earth, which takes 365 days to circle the Sun, WASP-12b is locked in an eternal race around its star. This means that every single day the planet completes a full lap, experiencing no real seasons as we do on Earth. However, such a tight orbit comes at a cost. The planet is subjected to immense stellar radiation, meaning that it is constantly bombarded with heat and energy from its star. This has devastating effects on its atmosphere, structure, and long-term survival. Because of its closeness to its star, WASP-12b experiences extreme temperatures. Scientists estimate that the planet's surface can reach well over 2,000 degrees Fahrenheit, making it hotter than molten lava. At these temperatures, even metals would vaporize, and any solid material would be reduced to gas. Such heat creates a planet where everything is in a state of constant chaos. The atmosphere is made up of gases that cannot exist in cooler conditions. This means that unlike Earth's atmosphere, which is made up of stable gases like oxygen and nitrogen, WASP-12b's atmosphere is highly volatile and constantly shifting. The intense heat also causes another strange phenomenon. The planet glows. Just as heated metal begins to radiate light, the surface of WASP-12b emits a faint glow due to the extreme temperatures. This eerie effect makes the planet appear as if it is on fire, giving it an otherworldly, almost hellish appearance. One of the most bizarre characteristics of WASP-12b is its unusual shape. Instead of being a perfect sphere like most planets, it is noticeably flattened at the poles and bulging at the equator. This happens because of the intense gravitational forces from its nearby star. Just as the moon affects Earth's tides, pulling on the ocean and causing waves, WASP-12b is being pulled by its star's powerful gravity. However, unlike Earth's oceans, this pull is so strong that it is actually stretching the entire planet. The result is an oblate or egg-like shape, making WASP-12b one of the most distorted planets ever observed. This intense stretching does more than just change the planet's shape. It also affects its internal structure. The constant gravitational tug creates enormous friction inside the planet, generating even more heat. This additional heating adds to the already extreme temperatures, making the atmosphere even more unstable. Perhaps the most astonishing aspect of WASP-12b's existence is that it is slowly being destroyed. Scientists have discovered that the planet is losing its atmosphere at an incredible rate, roughly 100 million tons of gas per year. This is happening because of the combination of extreme heat and powerful stellar winds. The intense radiation from the star causes the planet's atmosphere to expand and become less dense. At the same time, strong winds from the star push against the atmosphere, stripping away layers of gas. Over time, this process is leading to the complete destruction of WASP-12b. Scientists estimate that in just a few million years, the planet will be entirely consumed by its star. In the grand scale of the universe, this is an incredibly short amount of time, making WASP-12b one of the most doomed planets ever discovered. As the planet continues to disintegrate, it leaves behind a trail of lost material, which forms a cloud of debris around its star. This offers astronomers a rare opportunity to study the effects of extreme planetary destruction. By observing WASP-12b, scientists can better understand how planets evolve, die, and sometimes even merge with their parent stars. If you could somehow stand on the surface of WASP-12b, though survival would be impossible, the sky would look unlike anything seen on Earth. The planet's parent star would appear enormous, blazing with an intense brightness that dominates the sky. Due to atmospheric scattering, the light could take on strange and fiery hues, ranging from brilliant white and yellow to deep shades of orange and red. The planet's atmosphere, filled with exotic gases, would likely swirl with chaotic cloud formations, constantly shifting due to powerful winds. These clouds could be tinted with shades of blue, purple, and even red, reflecting the intense radiation from the star. The intense heat might also cause frequent storms, with violent winds sweeping across the planet at thousands of miles per hour. These storms could churn up towering plumes of gas, stretching high into the sky and creating a hauntingly beautiful but deadly environment. At night, if it can even be called night, the sky would likely remain aglow with a faint reddish or orange light due to the extreme heat radiating from the surface. Unlike Earth, where we can gaze at distant stars, the brightness of the parent star and the thick atmosphere would likely block out most of the cosmos, making it nearly impossible to see anything beyond the planet's immediate surroundings. The story of WASP-12b is more than just a tale of a doomed planet. It is a lesson in the forces that shape the universe. This exoplanet gives scientists a glimpse into the powerful effects of extreme gravity, heat, and radiation, offering valuable insights into how planets evolve under harsh conditions. It also raises intriguing questions about the fate of other planets. Could there be Earth-like planets orbiting their stars in a similar manner? Could our own planet ever experience such extreme changes billions of years in the future? By studying worlds like WASP-12b, astronomers can begin to piece together the puzzle of planetary life cycles, helping us understand both our past and our future in the cosmos. WASP-12b is a fascinating exoplanet that exists in an incredibly hostile environment. This alien world orbits so close to its parent star that it is constantly exposed to extreme heat, making it one of the hottest planets ever discovered. Its surface temperature is estimated to reach nearly 2,500 degrees Celsius, which translates to about 4,500 degrees Fahrenheit. At these blistering temperatures, nothing remains in a solid or even liquid state. Everything is vaporized into gas. Unlike Earth, where metals like iron and copper exist as sturdy solids, on WASP-12b, they cannot hold their shape. Instead, they are instantly turned into gas, creating an environment where even elements with high melting points, such as lead, exist as vapors. This results in a planet that lacks the familiar solid surfaces we are used to. Instead of land, oceans, or mountains, the entire surface of this planet is a chaotic storm of superheated gases. But what makes this exoplanet even more mysterious is its eerie glow. The intense heat from its star causes its atmosphere to be filled with exotic gases such as sodium and potassium, which, under these extreme conditions, create a unique luminous effect. As a result, WASP-12b reflects its star's light in a way that makes it stand out, almost as if it were a burning ember drifting through space. WASP-12b is not just suffering from extreme heat, it is also in the process of slowly being torn apart. Because it orbits so close to its parent star, the immense gravitational forces exert a powerful pull on the planet. This effect is so strong that it stretches the planet into an elongated shape, distorting its structure. More importantly, this gravitational pull is steadily stripping away the planet's atmosphere. The radiation from the star heats up the gases in the atmosphere to such a degree that they start escaping into space. Lighter elements such as hydrogen and helium are the first to be lost, but over time even heavier elements may follow. This process, known as atmospheric escape, is reshaping the planet, making it smaller and less stable over time. The powerful stellar winds further accelerate this process. These winds, composed of high-energy particles ejected by the star, bombard WASP-12b's atmosphere, pushing gases away and eroding its outer layers. If this continues for millions of years, the planet could lose a significant portion of its mass, possibly leaving behind only a dense, rocky core. The harsh conditions of WASP-12b mean that its surface and atmosphere are in a constant state of transformation. With each passing orbit, more material is stripped away, and the planet's overall structure is altered. Scientists believe that studying this process in real time provides a rare glimpse into how extreme planets evolve. For example, WASP-12b is classified as a hot Jupiter, a gas giant similar in composition to Jupiter but located much closer to its star. However, unlike our own Jupiter, which remains stable, WASP-12b is experiencing rapid atmospheric loss. Observing this phenomenon allows scientists to predict what might happen to other exoplanets in similar extreme conditions. The combination of intense heat, atmospheric escape, and gravitational stretching makes WASP-12b one of the most volatile and unstable planets ever observed. It serves as a natural laboratory for understanding how planets can change over time due to their proximity to a star and the external forces acting upon them. The relationship between WASP-12b and its star is a dramatic example of the power of celestial mechanics. The star's gravity not only pulls on the planet, but also creates immense tidal forces, stretching it like a piece of putty. This tidal stretching contributes to the gradual breakdown of the planet's atmosphere, further increasing the rate at which gases are lost to space. The gravitational forces also indirectly affect the planet's temperature. As the atmosphere gets ionized by the star's radiation, some particles are propelled even farther away. This means that WASP-12b is losing material from both its surface and upper atmosphere at an alarming rate. Studying WASP-12b is crucial for understanding the life cycle of planets, especially those known as hot Jupiters. Scientists are particularly interested in how long these planets can retain their atmospheres before they are stripped down to a barren core. By observing WASP-12b, researchers can make predictions about the fate of other similar exoplanets and even gain insights into how planetary systems evolve over billions of years. This research also helps scientists determine the conditions required for a planet to maintain its atmosphere for an extended period. Many exoplanets may start their lives with thick, dense atmospheres, but gradually lose them due to stellar radiation and gravitational interactions. Some may eventually end up resembling Mercury or Earth's moon, dry, rocky bodies devoid of any gaseous envelope. If a spacecraft were ever able to survive the extreme heat of WASP-12b and send back data, it would witness an environment unlike anything in our solar system. The planet's upper atmosphere is an ever-changing mixture of hydrogen, helium, sodium, and other volatile gases, all swirling in a superheated haze. The surface, if it can even be called that, is nothing more than a vast expanse of vaporized metals and elements constantly shifting under the influence of extreme temperatures and powerful stellar winds. Over time, WASP-12b may continue to lose so much mass that it becomes unrecognizable from its current form. It might shrink into a smaller, denser planet, or, in an even more dramatic scenario, it could eventually be fully consumed by its star, leaving behind only traces of its existence. As a spacecraft enters the upper layers of the atmosphere on the distant exoplanet WASP-12b, it would face rapidly changing conditions. Unlike the Earth's atmosphere, which remains relatively stable, the atmosphere of this alien world is dynamic and constantly shifting. It consists of multiple layers, each with different levels of pressure and density. These layers do not remain in one place. Instead, they move due to the planet's intense heat and the powerful radiation emitted by its nearby star. This constant motion creates strong and unpredictable wind patterns, which could make it difficult for a spacecraft to maintain a steady course. The force of these winds could push the spacecraft off its intended trajectory, making navigation a significant challenge. Stabilizing the spacecraft would require advanced technology capable of adjusting for sudden atmospheric changes in real time. Aside from battling turbulent winds, the spacecraft would also encounter strange chemical reactions occurring within the atmosphere. The extreme radiation from the planet's star interacts with various elements present in the air, leading to fascinating and unusual phenomena. Elements such as sodium and potassium, which are commonly found on Earth, behave differently on WASP-12b. These elements can absorb the intense light from the star and then re-emit it, creating bright, glowing trails that streak across the sky. This reaction could result in breathtaking visual effects, with the entire atmosphere appearing to shimmer in an otherworldly glow. The high levels of radiation also energize particles in the air, producing vibrant colors that would make the sky of WASP-12b look completely alien compared to what we see on Earth. The extreme heat of this exoplanet also leads to another bizarre occurrence: clouds made of vaporized metals. On Earth, metals like iron and aluminum exist as solid materials or at most melt into liquid under high temperatures. However, the intense heat of WASP-12b is so extreme that even these dense substances can exist as gases, forming metallic clouds that drift across the sky. Observing these unique atmospheric features would provide scientists with groundbreaking information about how planets in other solar systems behave under extreme conditions. Studying these processes would help researchers understand not only the nature of WASP-12b, but also the diversity of atmospheres that exist beyond our own solar system. The future of WASP-12b is vastly different from what is expected for Earth and the other planets in our solar system. This exoplanet is orbiting extremely close to its parent star, a situation that exposes it to relentless gravitational and radiation forces. Over time, these forces are stripping away its atmosphere, causing the planet to slowly lose mass. If this process continues, the planet may eventually be reduced to little more than a lifeless, barren rock. The extreme conditions make it unlikely that WASP-12b could ever support any form of life as we understand it. In contrast, our solar system follows a different path of evolution. The planets in our system orbit at various distances from the Sun, experiencing vastly different environments. Scientists predict that over the next several billion years, the Sun will gradually burn through its nuclear fuel. Once this happens, it will expand into a massive red giant, a phase that could have catastrophic consequences for the inner planets, including Earth. As the Sun grows larger, it may engulf Mercury, Venus, and possibly even Earth. If this occurs, our planet will be completely destroyed, much like WASP-12b, but over a much longer period of time. The outer planets, such as Jupiter and Saturn, might experience shifts in their orbits due to the Sun losing mass as it expels its outer layers. While this transformation will drastically change the solar system, the process will take place over billions of years, allowing for a more gradual transition. Unlike WASP-12b, which is facing rapid destruction, the planets in our solar system will have more time to adapt to their changing environment before their ultimate fate is sealed. By studying WASP-12b, scientists can gain valuable insights into the different paths that planets can take. Some worlds, like Earth, may exist for billions of years before undergoing dramatic changes, while others, like WASP-12b, are doomed to a far more rapid and violent end. This research reinforces the idea that the fate of a planet is deeply tied to its relationship with its parent star. Some planets are fortunate enough to have stable conditions for long periods, while others face an early demise due to extreme heat and radiation. Among these celestial bodies, one exoplanet stands out for a truly bizarre reason. It is darker than anything astronomers have ever seen. This planet, known as TRES-2b, has earned the title of the darkest known planet because of its incredible ability to absorb nearly 97% of the light that reaches its surface. To put that into perspective, it is even darker than coal, black acrylic paint, or the deepest shadows cast on Earth. When scientists look at this planet through telescopes, it appears almost like a black hole, an eerily dark void floating in space. But what makes TRES-2b so dark? The secret lies in its unusual atmosphere, which is believed to contain exotic chemicals that trap and absorb light rather than reflecting it. This makes the planet appear nearly pitch black, with only a faint reddish glow caused by its searing heat. If you were somehow able to stand on this planet's surface, which would be impossible due to its extreme conditions, you would see a world so dark that even nearby objects would barely be visible. Unlike Earth, where sunlight bounces off surfaces and illuminates everything around us, TRES-2b seems to swallow light completely, creating an environment that feels both alien and unsettling. TRES-2b's darkness can be explained by the strange chemical makeup of its atmosphere. Researchers believe that its air is filled with light-absorbing substances, possibly including metallic clouds and vaporized elements like sodium and potassium. These elements act almost like a powerful black coating, preventing light from escaping. Unlike planets like Earth or Venus, which have clouds that reflect sunlight, TRES-2b's atmosphere works in the exact opposite way. It absorbs light, making the planet look as if it barely exists. Additionally, scientists suspect that carbon-rich compounds, such as carbon monoxide and carbon dioxide, may also play a role in this phenomenon. These gases could create a dense, layered atmosphere that prevents light from escaping, reinforcing the planet's dark and ghostly appearance. Some theories even suggest the possibility of unknown chemicals that could be responsible for such an extreme level of light absorption. After all, the universe is full of mysteries, and TRES-2b is a prime example of how much we still have to learn. What makes TRES-2b even more fascinating is how different it is from most planets in our own solar system. While some planets and moons, like Saturn's moon Titan, have dark surfaces, none come close to the level of darkness seen on TRES-2b. Even the darkest planets in our solar system reflect at least some light back into space, giving them at least a faint glow. TRES-2b, however, is so dark that it appears as a void, standing in stark contrast to the bright and colorful planets we are used to. To understand just how extreme this is, let's compare it to Earth. Our planet reflects about 30% of the sunlight that hits it, which is why we see blue oceans, white clouds, and green forests. Even the moon, which appears dark in some photos, reflects about 12% of sunlight. TRES-2b, however, absorbs nearly all the light that hits it, making it a truly alien world. Despite its intense darkness, TRES-2b is anything but cold. In fact, it is one of the hottest exoplanets ever discovered, with surface temperatures reaching a staggering 2,700 degrees Fahrenheit, hot enough to melt most metals. This extreme heat is due to its proximity to its parent star, as TRES 2b is classified as a hot Jupiter, a type of gas giant that orbits very close to its sun. Because of this closeness, the planet is bombarded with intense stellar radiation, causing its atmosphere to heat up dramatically. Yet instead of reflecting some of this energy back into space, as lighter-colored planets do, TRES 2b absorbs almost all of it. This makes the planet even hotter, effectively turning it into a burning black sphere that glows faintly due to the sheer amount of heat it retains. Additionally, the light-absorbing materials in its atmosphere may act like a greenhouse effect on steroids, further trapping heat and preventing it from escaping. This means that, unlike Earth, where heat is distributed through winds and ocean currents, TRES 2b's atmosphere locks in heat, creating a hellish and inhospitable environment. At first glance, TRES 2b might just seem like a strange, dark planet floating in space, but its discovery has major implications for astronomy. By studying exoplanets like this one, scientists can learn more about the many different types of worlds that exist beyond our solar system. Understanding what makes TRES 2b so dark helps researchers uncover new chemical processes that may occur in extreme planetary atmospheres. Additionally, TRES 2b serves as a reminder of the vast diversity of planets in the universe. While we are used to seeing planets with bright atmospheres and reflective clouds, the cosmos is filled with planets that defy expectations. TRES 2b is just one of many examples of how alien and unpredictable the universe can be. Furthermore, studying the atmospheric composition of planets like TRES 2b could help astronomers identify potential signs of life elsewhere in the universe. While this particular planet is far too hostile to support life, the methods used to analyze its atmosphere can be applied to other exoplanets, especially those that may have Earth-like conditions. TRES 2b, an exoplanet located far beyond our solar system, presents conditions that would be utterly overwhelming for humans. If someone were to step onto this world, they would experience scorching temperatures, nearly complete darkness, and an atmosphere that absorbs light rather than reflecting it. This planet, unlike anything we see on Earth, challenges our understanding of how planetary environments can vary across the universe. The heat on TRES 2b is beyond anything we could survive without advanced protection. The planet's surface temperature soars to approximately 1,500 degrees Celsius. To put that into perspective, it is even hotter than the molten lava that erupts from Earth's most active volcanoes. This extreme temperature would immediately incinerate any unprotected material, let alone a human being. The only way to endure such an infernal environment would be through the use of highly advanced heat-resistant suits. Even then, exposure would have to be brief, as the extreme conditions could still damage equipment over time. But why is TRES 2b so incredibly hot? The answer lies in its proximity to its parent star. The planet orbits its star at an extraordinarily close distance, meaning it is constantly bombarded with intense radiation and heat. Unlike Earth, which has a protective atmosphere to regulate temperature, TRES 2b absorbs nearly all the energy it receives, creating a blistering landscape that never cools down. One of the most mysterious features of TRES 2b is its darkness. On Earth, we rely on light reflecting off surfaces to see our surroundings. However, on this distant exoplanet, the situation is very different. The atmosphere of TRES 2b is filled with metallic compounds and vaporized elements that absorb light, rather than bouncing it back into space. As a result, the planet appears pitch black, even though it is so close to its star. Imagine walking through a dense fog on Earth at night, but instead of mist, you are surrounded by an eerie, inescapable darkness. Even powerful flashlights would struggle to penetrate the blackness because the atmosphere absorbs most of the light before it can illuminate anything. The only way to navigate would be through the use of advanced imaging technology, possibly using infrared or thermal cameras to detect heat instead of relying on visible light. Because TRES 2b absorbs nearly all the light that reaches it, the human eye would have a hard time adjusting to such an environment. On Earth, we see things by perceiving the contrast between light and shadow. But on this planet, the lack of reflected light would make it almost impossible to discern shapes or distances. This means that even if an astronaut were standing right in front of a large rock formation, they might not see it at all unless they touched it. For humans, the experience would be similar to being in a completely dark cave with no light source. Even if someone were to carry an artificial light, its effectiveness would be significantly reduced due to the atmosphere's ability to absorb it. This creates an environment where navigation is not only challenging, but potentially disorienting and dangerous. Given its bizarre characteristics, how do scientists study a planet that is so far away and so difficult to observe? The answer lies in a sophisticated technique called transit photometry. This method involves monitoring a star and looking for small temporary drops in brightness. These dips in light occur when a planet passes in front of the star, partially blocking its light. By analyzing how much light is blocked, researchers can determine the size of the planet and how much light it reflects. For TRES 2b, scientists have found that its albedo, the measure of how much light a surface reflects, is extremely low. In fact, it reflects less than 1% of the light that reaches it. This is lower than charcoal or even the darkest artificial black paints created in laboratories on Earth. The planet is essentially a cosmic black hole in terms of visibility, absorbing nearly all the light that touches it. While transit photometry helps measure a planet's reflectivity, another important method used is spectroscopy. This technique involves studying the way light interacts with a planet's atmosphere. As light from the star passes through the planet's gaseous envelope, certain wavelengths are absorbed by the chemicals present. By breaking this light into its individual components, much like a prism creating a rainbow, scientists can identify what elements are in the atmosphere. Additionally, both ground-based and space telescopes monitor exoplanets in different wavelengths of light. By tracking changes in brightness, astronomers can gather more details about the planet's temperature, atmospheric composition, and overall properties. These combined methods allow scientists to construct a clearer picture of what a planet like TRES 2b is truly like, despite it being light years away from us. The study of TRES 2b provides valuable insight into how planets form and evolve. One of the key lessons is how a planet's proximity to its star influences its atmospheric conditions. Because TRES 2b is so close to its parent star, it experiences extreme heating that alters its chemical makeup. This process, known as atmospheric escape, means that lighter gases are constantly being stripped away and lost to space. Over time, this can dramatically change the planet's environment, leaving behind only the heaviest, most heat-resistant compounds. Additionally, the presence of metallic elements in TRES 2b's atmosphere helps scientists understand how different materials interact with heat and light. The planet's ability to absorb nearly all light shows how atmospheric composition plays a crucial role in determining a planet's appearance and climate. One of the most defining features of TRES 2b is its incredibly close orbit around its host star. Unlike Earth, which takes 365 days to complete a journey around the Sun, TRES 2b completes its orbit in just a fraction of that time, less than 2 days. This means it is locked in a perpetual struggle against the intense heat and radiation coming from its nearby star. Because the planet is so close to its star, its temperature soars to around 1,500 degrees Celsius. At such extreme temperatures, many elements and compounds that would be solid or liquid on Earth instead turn into gas, creating an atmosphere filled with exotic metallic clouds. These clouds contain substances that are particularly good at absorbing light, which is a big reason why TRES 2b appears so dark. Instead of reflecting sunlight like Earth does with its oceans and clouds, this planet absorbs nearly all the light that hits it, making it look like a pitch-black void in space. Most planets, including gas giants like Jupiter, reflect a certain amount of light from their stars. Even the darkest planets in our solar system, such as Mercury or Venus, reflect at least a small percentage of sunlight. However, TRES 2b defies expectations by reflecting less than 1% of the light that reaches it. In comparison, coal or black asphalt on Earth still reflects more light than this eerie world. Scientists believe that the reason behind this extreme darkness lies in its unique atmospheric composition. The superheated environment of TRES 2b allows certain light-absorbing materials, possibly metallic vapors like titanium oxide or sodium, to dominate the atmosphere. These materials act like a cosmic sponge, soaking up almost all incoming light rather than bouncing it back into space. Additionally, TRES 2b is a tidally locked planet, meaning that the same side always faces its star, while the other side remains in eternal darkness. This lack of rotation prevents the planet from distributing heat evenly, further intensifying its already extreme climate. The side facing the star is constantly bombarded with energy, making it even harder for the planet to reflect light. If we could somehow visit TRES 2b, we would witness an alien world where the weather is unlike anything seen on Earth. Due to its intense heat and the presence of metallic vapors, its atmosphere is likely filled with raging storms, powerful winds, and possibly even metallic rain. Since the planet is tidally locked, its extreme temperature differences create powerful wind currents. The superheated atmosphere on the bright side expands and rises, while cooler air from the dark side rushes in to take its place. This constant movement of air could create winds traveling thousands of kilometers per hour, far stronger than any hurricane on Earth. Additionally, some scientists speculate that molten metal droplets might condense in the upper atmosphere and fall as a kind of iron rain. Instead of water-based precipitation like we experience on Earth, TRES 2b's rain could be made of liquid iron or other heavy elements, which would instantly evaporate as they reach the scorching lower atmosphere. The night side of the planet, meanwhile, experiences no direct sunlight at all. This lack of warmth means temperatures there could be much lower than the day side, creating violent temperature contrasts that could lead to unpredictable weather patterns. These extreme conditions make TRES 2b an incredibly volatile world where the sky is likely filled with swirling clouds of metallic gas, and storms of molten iron may rage for days or even weeks at a time. One of the biggest questions in astronomy is whether life could exist beyond Earth. Given how extreme TRES 2b's environment is, it might seem like life would be impossible there. After all, life as we know it requires energy, stability, and protection from harmful radiation, none of which seem to be available on this dark planet. One of the biggest obstacles to life on TRES 2b is the fact that it absorbs nearly all light, meaning there is almost no visible sunlight reaching the planet's surface. This makes photosynthesis, the process by which plants and other organisms convert sunlight into energy, impossible. Without sunlight, any potential life forms would need to rely on other sources of energy, such as heat from the planet's interior or chemical reactions in its atmosphere. On Earth, we have discovered microorganisms called extremophiles that survive in incredibly harsh environments, such as deep-sea hydrothermal vents, where temperatures can exceed hundreds of degrees Celsius. If life exists on TRES 2b, it would likely have to be even more resilient than these Earth-based extremophiles, thriving in complete darkness, withstanding scorching temperatures, and surviving exposure to potentially toxic atmospheric chemicals. That being said, TRES 2b is a gas giant, meaning it likely has no solid surface. If life were to exist there, it would have to float in the dense atmosphere, much like some microscopic organisms do in Earth's clouds. However, given the extreme heat and the lack of a solid foundation for ecosystems to develop, the chances of life existing on this planet remain very slim. Studying TRES 2b is no easy task. Since the planet absorbs nearly all the light that reaches it, scientists cannot observe it directly using traditional telescopes. Instead, they rely on indirect methods, such as detecting how the planet's gravity affects its star or measuring the heat it emits in infrared wavelengths. One of the main challenges of exploring such a dark planet is that spacecraft and telescopes rely on light to gather information. Since TRES 2b reflects almost nothing, imaging the planet is extremely difficult. Instead, scientists use infrared sensors which can detect heat emissions and help reveal details about the planet's atmosphere and temperature. Another issue is communication and data transmission. Since TRES 2b orbits a distant star far beyond our solar system, sending signals back and forth would take a long time. Any future mission to study this planet would require advanced technologies capable of gathering data in extremely low-light conditions. Despite these challenges, astronomers continue to study TRES 2b using powerful space telescopes like NASA's James Webb Space Telescope. By analyzing how light behaves when passing through the planet's atmosphere, scientists hope to uncover even more secrets about this dark and mysterious world. TRES 2b is one of the strangest and most fascinating planets ever discovered. Its extreme darkness, intense heat, and violent weather patterns make it a place unlike anything we've seen in our own solar system. While the conditions on TRES 2b are incredibly hostile, its study provides valuable insights into how planets can form and evolve in different parts of the universe. If a planet has a thick atmosphere or is surrounded by floating space debris, these barriers could make communication even more difficult. Sending and receiving signals would be a challenge, and scientists would have to come up with smart ways to stay connected with any spacecraft exploring the planet. Studying the planet's surface would also require highly innovative approaches. Rovers and landers would need to be designed to handle rough, uneven landscapes, many of which might be covered in constant darkness. This means engineers would have to build machines that are not only tough and durable, but also equipped with advanced navigation systems to help them move safely in such challenging conditions. If scientists wanted to collect samples or analyze the surface, they would have to rely on tools and instruments capable of working efficiently in low-light environments. This could involve using autonomous systems, machines that can operate on their own without needing constant instructions from Earth, to make sure everything runs smoothly. Another crucial factor would be understanding the environmental conditions of this dark world. The planet could have extreme temperatures, an unpredictable atmosphere, or even toxic gases. To ensure a spacecraft can survive, scientists would need to create protective shields and materials that can withstand freezing cold, crushing atmospheric pressure, or dangerous chemicals. All of these challenges highlight just how complex and impressive the technology behind such a mission would need to be. Exploring a planet hidden in perpetual darkness would require incredible ingenuity, groundbreaking engineering, and a deep understanding of the unknown. The universe is full of mysteries, and strange matter is one of the most intriguing of them all. When we think about matter, we usually imagine things made of atoms, like people, animals, planets, and stars. But the universe contains much stranger types of matter, one of the most fascinating being strange matter. This unusual substance, also known as strange quark matter, is believed to exist under extremely high pressure and density, conditions so extreme that they are found only in the deepest cores of neutron stars or in hypothetical objects called strange stars. Some scientists also speculate that tiny droplets of strange matter, called strangelets, could exist freely in space or even on Earth. To understand strange matter, we need to break down the different types of matter in the universe, starting with the most familiar and working our way to the strangest. The kind of matter we interact with daily is called ordinary matter or atomic matter. It is made up of tiny building blocks called atoms. Every object, from a grain of sand to a massive planet, is made of atoms. But if we look even closer, we find that atoms themselves are mostly empty space, with almost all of their mass concentrated in their cores called atomic nuclei. Atomic nuclei are made up of two types of particles: protons, positively charged particles; neutrons, neutral, having no charge particles. These protons and neutrons are, in turn, made of even smaller particles called quarks. The two most common types of quarks in the universe are up quarks and down quarks. Each photon contains two up quarks and one down quark, while each neutron contains two down quarks and one up quark. The way these quarks interact determines the structure of atomic nuclei and ultimately everything we see around us. When we gather many protons and neutrons together, they form a special type of matter called nuclear matter. This is the substance that makes up the core of atoms and is found inside the nuclei of every element in the periodic table. It exists in a dense, liquid-like state where the protons and neutrons move freely but stay bound together by powerful forces. However, under extreme pressure, such as in the core of neutron stars, something extraordinary happens. Nuclear matter can be crushed so tightly that protons and neutrons break apart into their fundamental building blocks, the quarks. This leads to the formation of a new type of matter called quark matter. Quark matter is a super-dense state of matter composed entirely of free quarks. Scientists believe that quark matter could exist in two forms: non-strange quark matter, made only of up and down quarks; strange quark matter contains up-down, and an additional type called strange quarks. This is where strange matter comes into the picture. Strange matter is a special kind of quark matter that contains an extra ingredient: strange quarks. While up and down quarks are found everywhere in the universe, strange quarks typically form only under extreme conditions. Scientists theorize that when nuclear matter is compressed beyond a critical density, such as inside neutron stars, protons and neutrons dissolve into quarks, forming quark matter. If the conditions are right, this quark matter can turn into strange matter. Some researchers believe that strange matter might even be the most stable form of matter in the universe, meaning that if it forms, it could exist indefinitely. A particularly intriguing idea in physics is called the strange matter hypothesis, also known as the Bodmer-Witten assumption. It suggests that strange matter is actually the true fundamental state of matter, more stable than even atomic or nuclear matter. If this is true, then everything we see around us, including our bodies, planets, and stars, is only in a temporary, less stable state. Given enough time or the right conditions, all atomic nuclei could potentially transform into strange matter. This transformation would happen through the creation of strangelets, tiny droplets of strange matter. If strangelets were to come into contact with ordinary atomic nuclei, they might trigger a chain reaction, gradually converting everything into strange matter. Thankfully, there is no strong evidence that such a transformation is happening naturally in the universe. However, some scientists believe that small amounts of strange matter might already exist, possibly formed during powerful cosmic events such as neutron-star collisions. There are a few places in the universe where strange matter could potentially be found: the core of neutron stars. Neutron stars are the remnants of massive stars that exploded as supernovae. They are incredibly dense, so dense that a single teaspoon of neutron star material would weigh billions of tons. Some scientists believe that in the core of these stars, the pressure is high enough to create strange matter. If enough strange matter forms, the entire neutron star could transform into a strange star. Strangelets in space. Tiny fragments of strange matter, called strangelets, might float through space, created by extreme cosmic events. If these strangelets reached Earth, they could potentially be detected in cosmic rays or by experiments searching for exotic particles. High-energy particle collisions. Scientists at places like the Large Hadron Collider, LHC, smash particles together at high speeds to study fundamental physics. Some theories suggest that strange matter could be briefly created in these experiments, though it would likely decay quickly. If strange matter truly exists and is more stable than ordinary matter, it could completely change our understanding of physics. It would mean that the universe might naturally prefer to exist in a strange matter state, rather than the atomic state we observe. This has led to some mind-blowing possibilities. If a strangelet were to collide with a neutron star, it could potentially trigger a full transformation into a strange star. If strange matter is stable, it might be possible to create and harness it for futuristic applications. However, this remains purely theoretical for now. Some scientists speculate that quark stars or strange stars could already exist, but they would be difficult to detect since they might look similar to neutron stars from a distance. At its core, strange matter is an extreme state of matter made up of quarks, the fundamental building blocks of protons and neutrons. It forms under conditions of immense pressure, where the forces holding ordinary matter together can no longer resist the overwhelming density. To understand how strange matter comes into existence, we need to explore an important concept in physics known as degeneracy pressure. This force is what prevents extremely dense objects, such as white dwarfs and neutron stars, from collapsing under their own weight. Imagine a crowded subway train at rush hour. If more people try to squeeze in, those already inside must move or be pushed into uncomfortable positions. In physics, particles such as electrons, neutrons, and quarks behave in a similar way. They follow a rule called the Pauli exclusion principle, which states that two identical particles, in this case quarks, cannot occupy the same place and have the same energy at the same time. As a result, when matter is squeezed under extreme pressure, the particles are forced into higher energy states. This increase in energy creates resistance, which is what we call degeneracy pressure. However, there comes a point when the pressure becomes so intense that the normal rules of matter begin to break down. At this stage, a new type of matter, quark matter, can form. When this happens inside a neutron star, something even more bizarre may occur. Some of the particles transform into a completely new type of quark, known as the strange quark. This process creates strange matter, a form of matter that may be even more stable than ordinary neutron star material. Neutrons, the particles that make up neutron stars, are built from two types of quarks: up quarks, which have a positive charge of 2/3 of the charge of an electron; down quarks, which have a negative charge of 1/3 of the charge of an electron. A neutron consists of two down quarks and one up quark. Because down quarks outnumber up quarks, they contribute more to the overall degeneracy pressure inside neutron stars. However, under extreme conditions, some of these down quarks can change into strange quarks. Why would this happen? The transformation occurs because it allows particles to rearrange themselves in a way that lowers their total energy. Even though strange quarks have a slightly higher mass than down quarks, they create new energy levels, making the system more stable overall. This process turns regular quark matter into strange matter. When a neutron star becomes dense enough to start forming quark matter at its core, it is called a hybrid star. Scientists suspect that such stars exist, but proving it is extremely difficult. This is because we do not yet know exactly how much pressure is required to trigger the transition from neutron matter to quark matter. Physicists estimate that this transition likely happens when the density inside a neutron star reaches nearly 100 times the density of an atomic nucleus. That means that a sugar cube-sized piece of neutron star material would weigh billions of tons. However, a more precise calculation remains elusive because of the extremely complex nature of the strong nuclear force that governs quarks. To make matters more complicated, our most advanced mathematical tools struggle to accurately predict the behavior of quarks under such extreme conditions. One method, called lattice quantum chromodynamics, QCD, could theoretically help, but it runs into an obstacle known as the Fermion sign problem, which makes the calculations incredibly difficult. If strange matter exists, where can we find it? Scientists believe that the best chance of discovering strange matter is during neutron-star mergers, the violent collisions between two neutron stars. When two neutron stars collide, the impact is so powerful that it sends shockwaves across the universe, releasing vast amounts of energy in the form of gravitational waves and high-energy light. During these cataclysmic events, some of the strange matter from the core of the stars could be ejected into space. If astronomers could detect this material before it decays, it could provide direct evidence of strange matter. However, there are two major challenges. The decay rate of strange matter is unknown. Scientists do not yet know how quickly strange matter breaks down once it is outside a neutron star. If it decays too fast, it may never reach our telescopes. Neutron star mergers are rare. There are only a handful of neutron star pairs close enough to Earth for us to study in detail. This makes finding strange matter even harder. One of the most fascinating possibilities in physics is the strange matter hypothesis. This idea suggests that nuclear matter, the material that makes up protons and neutrons, is actually metastable, meaning it is not the most stable form of matter. Instead, it could theoretically decay into strange matter over an extremely long period. If this hypothesis is true, it could mean that strange matter exists naturally in the universe in several forms: quark stars, strange stars. Unlike hybrid stars, which only have a quark core, a quark star is entirely made of strange matter from its center to its surface. These bizarre objects would be only a few kilometers wide, but would contain an enormous amount of mass. They might even have a thin crust of ordinary nuclear matter on their surface. Strangelets. These are tiny pieces of strange matter, possibly as small as atomic nuclei. Scientists theorize that strangelets might be created when strange stars form, collide, or when a nucleus undergoes an unusual type of decay. If strangelets exist, they could potentially travel through space and even reach Earth. While no one has yet detected a quark star or a strangelet, researchers continue to search for evidence. If the strange matter hypothesis is correct, it could fundamentally change our understanding of the universe. Radiation is a mysterious form of energy that travels through space in waves or as moving particles. It is categorized into two main types: ionizing radiation and non-ionizing radiation. This classification depends on how much energy the radiation carries and its ability to affect atoms and molecules. Ionizing radiation is the more powerful type. It has enough energy, greater than 10 electron volts, to knock electrons out of atoms, which turns them into electrically charged particles called ions. This process, known as ionization, can break chemical bonds, which is why ionizing radiation can be harmful to living organisms. Common sources of ionizing radiation include radioactive materials, which release different types of radiation. Alpha radiation, made up of helium nuclei, 2 protons and 2 neutrons. Beta radiation consists of high-speed electrons or positrons. Gamma radiation, a form of high-energy light, photons. X-rays used in medical imaging. Cosmic rays, which come from space and interact with Earth's atmosphere to produce secondary radiation, including muons, mesons, neutrons, and positrons. Gamma rays, X-rays, and the high-energy part of ultraviolet light form the ionizing part of the electromagnetic spectrum. These waves have enough energy to remove electrons from atoms. The lower-energy ultraviolet light, although not strong enough to ionize atoms, can still damage molecules, leading to effects like sunburn. Non-ionizing radiation, the lower-energy form that heats things up. Non-ionizing radiation carries less energy and cannot remove electrons from atoms. Instead, it affects molecules by making their atomic bonds vibrate. This vibration produces heat, which is how microwave ovens warm food, and how infrared radiation from the sun keeps Earth warm. Although non-ionizing radiation is generally safer than ionizing radiation, excessive exposure can still be harmful. For example, prolonged exposure to ultraviolet light can cause skin damage and increase the risk of skin cancer. The word radiation comes from the way energy spreads outward from a source in all directions, similar to ripples in a pond. Because of this, radiation follows a predictable pattern as it moves through space. One important rule in physics is the inverse square law, which states that the intensity of radiation decreases as you move farther from its source. If you double the distance from a radiation source, the intensity becomes 4 times weaker. This is why standing farther away from a radioactive object significantly reduces exposure. When ionizing radiation strikes living cells, it can damage important molecules, including DNA. Since DNA contains the instructions for cell function and reproduction, damage to it can lead to cell death. If too much damage occurs, the cell cannot repair itself and dies. Mutations, changes in DNA that can cause uncontrolled cell growth, leading to cancer. The likelihood of developing cancer from ionizing radiation depends on the amount of radiation absorbed, measured in doses, the type of radiation, some types are more damaging than others, the sensitivity of the exposed tissue or organ, some body parts are more vulnerable. Even though a single exposure may only ionize a small fraction of atoms in a cell, repeated or intense exposure increases the risk of long-term damage. In addition to electromagnetic waves, radiation can also come in the form of particles, especially from radioactive materials and nuclear reactions. This type of radiation consists of high-speed subatomic particles that can collide with atoms, causing ionization. Alpha particles, large and slow-moving, can be blocked by a sheet of paper. Beta particles, faster and smaller, can penetrate materials like plastic or thin metal. Neutrons. Unlike other types, neutrons have no electrical charge, allowing them to penetrate deep into materials. Protons. High-energy protons can also cause ionization. Because particle radiation has mass and momentum, it is powerful enough to knock electrons out of atoms. However, most of these particles do not travel far through matter, except for neutrons, which can penetrate deeply. Radiation is naturally present in the environment. Some of it comes from outer space as cosmic rays, while other sources include the Earth's soil and rocks, which contain small amounts of radioactive materials. Since ionizing radiation is invisible and cannot be detected by human senses, special instruments like Geiger counters are used to measure radiation levels. In some cases, radiation can cause materials to glow or emit light, such as Cherenkov radiation, a blue glow seen in nuclear reactors, radioluminescence, used in glow-in-the-dark materials. Although radiation can be dangerous, it is also useful in medicine, research, and industry. X-rays, for example, help doctors diagnose diseases, while radiation therapy is used to treat cancer. However, improper exposure to high doses can lead to serious health effects. Radiation exposure can cause harm in several ways. Short-term exposure to high levels of ionizing radiation can result in acute radiation syndrome, ARS, with symptoms such as skin burns, hair loss, damage to internal organs, and in severe cases, death. Even low doses of ionizing radiation carry risks. Long-term exposure increases the chance of developing cancer, particularly thyroid cancer when exposed to radioactive iodine. The exact risk of cancer from radiation is still not completely understood, but studies of survivors from nuclear bombings and reactor accidents, such as Hiroshima, Nagasaki, and Chernobyl, provide some of the best available data. The International Commission on Radiological Protection acknowledges that radiation risk calculations involve uncertainties. They emphasize that population-based estimates are useful for large-scale studies, but may not be precise for individual risk assessment. The Earth's atmosphere acts as a protective shield against certain types of radiation. For example, high-energy ultraviolet light, which can ionize air molecules, is absorbed by the ozone layer. This means that some of the most dangerous ultraviolet radiation never reaches Earth's surface. Scientists refer to this highly energetic ultraviolet light as vacuum ultraviolet, since it is mostly found in space. While it plays a role in astrophysics, it does not have much biological importance because it does not reach living organisms. The world around us is filled with different types of radiation, some of which are harmless while others pose serious risks. Radiation can come from natural sources like the sun or artificial ones like X-ray machines. In this explanation, we'll break down the different types of radiation in an easy-to-understand way while expanding on their effects and importance. The ozone layer is a protective shield high up in the Earth's atmosphere. It begins at about 20 miles, which is approximately 32 kilometers, above the Earth's surface and stretches even higher. This layer plays a crucial role in absorbing nearly 98% of the most harmful types of ultraviolet, UV radiation, UVB and UVC. Ultraviolet radiation is a form of energy that comes from the sun. Although it is not strong enough to ionize atoms, which means it does not completely remove electrons from them, it still has enough energy to excite molecules, leading to harmful effects. One significant impact of ultraviolet radiation is the damage it causes to DNA. When DNA absorbs this energy, it can lead to the formation of pyrimidine dimers, a type of mutation that can interfere with the normal functioning of cells and even cause cancer. This damage begins to occur at wavelengths shorter than 365 nanometers, which is well below the energy needed to ionize atoms. Unlike ultraviolet radiation, visible light and longer wavelength energy forms, such as infrared, microwaves, and radio waves, carry much lower energy per photon. Because they do not have enough energy to excite or damage biological molecules, they are considered much safer for living organisms. X-rays are a more powerful form of radiation than ultraviolet light. These waves have a very short wavelength, less than 1/billionth of a meter, and an extremely high frequency, exceeding 300 quadrillion cycles per second. Their energy is strong enough to interact with atoms in a way that can either move electrons to higher energy levels or completely remove them, which is called ionization. When X-rays pass through the human body, different tissues absorb them at different rates. Bones, which contain large calcium atoms, absorb more X-ray energy than soft tissues, which are made up of smaller atoms. This difference is what allows doctors to take X-ray images where bones appear white while soft tissues remain darker. X-ray machines take advantage of this contrast to help detect fractures, tumors, or other medical conditions. Although the sun produces some X-rays, none of them reach the Earth's surface because our atmosphere absorbs them entirely. This is a good thing because prolonged exposure to X-rays can be harmful to living organisms. Gamma rays are even more energetic than X-rays. They have wavelengths smaller than 3/10 trillionths of a meter and frequencies above 10 quintillion cycles per second. Unlike X-rays, which can be generated by machines, gamma rays come from nuclear reactions, processes that occur inside the nucleus of an atom. These high-energy waves are released when an unstable atomic nucleus sheds excess energy. Unlike alpha and beta radiation, which consist of particles with mass and electric charge, gamma radiation is purely energy. This allows gamma rays to penetrate deeply into materials, making them extremely difficult to block. Although gamma rays can pass through many substances, they can be significantly reduced by dense materials such as lead or depleted uranium. Even Earth's atmosphere is effective at stopping gamma rays from outer space, ensuring that these powerful waves do not reach the planet's surface. However, gamma rays still pose a significant risk in certain situations, such as in nuclear accidents or during radiation therapy treatments. Alpha particles are large, heavy particles consisting of 2 protons and 2 neutrons, essentially the core of a helium atom. Because they are heavy and carry a strong positive charge, alpha particles interact intensely with matter, losing their energy quickly. In the air, alpha particles can only travel a few centimeters before stopping, and they can be blocked by a thin sheet of paper or even the dead outer layer of human skin. This means that under normal conditions, they do not pose a threat to human health. However, if alpha-emitting substances, such as radium, radon, or polonium, are inhaled or swallowed, they become extremely dangerous. Once inside the body, Alpha particles can damage living tissues and DNA, increasing the risk of cancer. In fact, alpha radiation is at least 20 times more damaging per unit of energy than X-rays or gamma rays when it comes into direct contact with internal tissues. In outer space, a small percentage of cosmic rays consist of very high-energy alpha particles. These can penetrate the human body and even thin metal shields, which is why astronauts are at greater risk of exposure to this type of radiation. However, on Earth, we are protected by both our planet's magnetic field and thick atmosphere. Beta radiation consists of fast-moving electrons, negatively charged particles, or positrons, positively charged particles, which are the antimatter counterpart of electrons. It is more penetrating than alpha radiation, but still less powerful than gamma rays. There are two types of beta radiation: beta-minus radiation. This happens when a neutron in an atom transforms into a proton and releases an electron, beta particle, and an antineutrino, beta plus radiation. In this case, a positron is emitted instead of an electron. When a positron collides with an electron, both particles annihilate each other, releasing two gamma photons in opposite directions. Because beta radiation is more penetrating than alpha particles, it requires denser materials for shielding. A few millimeters of metal or a few centimeters of plastic can effectively stop beta particles. In medicine, beta radiation is sometimes used in radiotherapy to treat certain types of cancer, particularly superficial tumors. Unlike all the other types of radiation discussed so far, neutron radiation does not consist of charged particles or electromagnetic waves. Instead, it is made up of free neutrons, which are neutral subatomic particles. Neutron radiation is relatively rare and mainly occurs during nuclear fission or fusion reactions. Large numbers of neutrons are released for a very short time, only about 10 millionths of a second, during events like a nuclear explosion or continuously in an active nuclear reactor. Once the reactor is shut down, neutron production stops almost immediately. Since neutrons do not carry an electric charge, they penetrate materials deeply, often more than gamma rays do. This makes neutron radiation particularly dangerous in nuclear settings, requiring special shielding materials such as water, concrete, or boron-containing compounds. Did you know that neutrons, tiny particles that exist in the nucleus of atoms, have the ability to turn other materials radioactive? This fascinating process is known as neutron activation. It is a major method used to create radioactive materials, which have a wide range of applications in medicine, research, and industry. What makes this process even more intriguing is that even slow-moving neutrons, called thermal neutrons, can activate materials quite effectively. Unlike charged particles such as electrons or protons, neutrons do not cause ionization by interacting with electrons in an atom. Instead, they are neutral, meaning they have no electrical charge. However, neutrons can be absorbed by atomic nuclei, making them unstable. Once an atom's nucleus becomes unstable, it can release radiation in the form of particles or energy. This is why neutrons are often referred to as indirectly ionizing. They do not ionize atoms in the usual way, but they still trigger radiation. Even neutrons that have very little kinetic energy, movement, are still capable of causing ionization, making them a significant radiation hazard. However, not every material can be easily activated by neutron radiation. Take water, for example. The two main elements in water, hydrogen and oxygen, can capture neutrons and become slightly heavier versions of themselves, but they do not turn radioactive in a meaningful way. It would take multiple neutron absorptions to activate hydrogen, which is extremely rare, and oxygen would need to absorb 2 additional neutrons. As a result, water is only very weakly radioactive when exposed to neutrons. On the other hand, some materials are highly susceptible to neutron activation. Sodium, which is found in salt, including sea salt, only needs to absorb a single neutron to transform into sodium-24, an intensely radioactive isotope. This isotope undergoes beta decay, a type of radioactive emission, and has a half-life of 15 hours. This means that after 15 hours, half of the sodium-24 atoms will have decayed into another form of matter, emitting radiation in the process. Neutrons that are moving at high speeds, also known as high-energy neutrons, are even more powerful. Unlike thermal neutrons, which mostly cause radiation through neutron activation, high-energy neutrons can also directly ionize atoms. One way they do this is by colliding with an atomic nucleus with such force that they knock the atom out of a molecule, breaking chemical bonds in the process. When this happens, electrons can be left behind, which means ionization has occurred. This process also leads to the creation of chemical free radicals, which are highly reactive molecules that can damage biological tissues. Another way high-energy neutrons ionize atoms is through a process known as neutron spallation, or knockout reactions. In this process, a neutron slams into an atomic nucleus, especially a hydrogen nucleus, causing it to eject a high-energy proton. This is similar to how a billiard ball transfers energy to another ball upon impact. The ejected protons, being positively charged, can then go on to directly ionize other atoms, making high-energy neutrons particularly dangerous. One of the biggest challenges with high-energy neutrons is that they can travel long distances. In open air, they can move for hundreds or even thousands of meters before losing energy. Even in solid materials, they can penetrate several meters deep. This is why they require thick shielding, often made of materials rich in hydrogen, such as water or concrete, to effectively block them. Inside a nuclear reactor, for instance, a several-meter-thick layer of water is used to shield against neutron radiation. While neutron radiation is common in nuclear reactors, there are also natural sources of high-energy particles that constantly bombard the Earth. These cosmic particles come from two main sources: the Sun. Our Sun continuously releases a stream of charged particles, mostly protons, in what is known as the solar wind. Occasionally, the Sun emits a huge burst of particles during events called coronal mass ejections, CMEs, which can greatly increase the flow of high-energy particles reaching Earth. Deep space, beyond our solar system. Some of the highest energy particles that reach Earth come from deep space, far beyond our own galaxy. These galactic cosmic rays are much less frequent than solar particles, but they carry much greater energy. Most of these particles are protons, with some being alpha particles, helium nuclei, and a few even heavier atomic nuclei. Scientists believe that these cosmic rays originate from some of the most violent events in the universe, such as supernovae, exploding stars, and gamma-ray bursts, GRBs, which involve intense magnetic fields that can accelerate particles to extreme speeds. Some theories also suggest that cosmic rays may come from quasars, which are enormous energy jets that existed in the early universe. Not all radiation is capable of ionizing atoms. Some forms of radiation do not have enough energy to knock electrons off atoms and are classified as non-ionizing radiation. This includes radio waves, microwaves, infrared light, and some forms of ultraviolet light. While non-ionizing radiation does not produce charged ions, it can still interact with matter in other ways. For example, it can change the way molecules vibrate or rotate, affecting their energy levels. Scientists are still studying how non-ionizing radiation affects biological tissues, but different types of radiation can have different effects on living organisms. Interestingly, even non-ionizing radiation can cause thermal ionization under extreme conditions. If a material absorbs enough heat, its atoms can reach high enough temperatures to become ionized. This is why fire can produce ionization, and why food turns brown when cooked under intense heat, such as when using infrared radiation in broiling. The electromagnetic spectrum refers to all the different types of electromagnetic radiation, arranged by their energy levels. Each object in the universe emits or absorbs electromagnetic radiation in a unique way, creating a signature spectrum. The non-ionizing part of the spectrum includes radio waves, used in communication such as television and radio signals, microwaves, used in microwave ovens and some types of wireless communication, infrared light, felt as heat, used in night vision devices, visible light, the part of the spectrum that humans can see. Ultraviolet light, lower energy, can cause chemical changes but does not fully ionize atoms. Higher energy radiation, such as X-rays and gamma rays, is completely ionizing. Even higher energy ultraviolet light can ionize atoms, despite the lower energy ultraviolet being classified as non-ionizing. Interestingly, while low energy ultraviolet light does not cause direct ionization, it can still damage biological molecules and increase the risk of cancer. This is why exposure to ultraviolet radiation from the sun can lead to sunburn, DNA damage, and mutations in skin cells. Infrared light, often called IR, is a type of electromagnetic radiation that falls between visible light and microwaves on the electromagnetic spectrum. It has wavelengths that range from a little over 7/10 of a micrometer, which is smaller than the width of a human hair, to 300 micrometers. This means that infrared light has a lower frequency than visible light, but a higher frequency than microwaves. One of the fascinating things about infrared radiation is that it can be sensed as heat even from a distance. For example, certain species of snakes, such as pit vipers, have special heat-sensing organs called pits on their heads. These pits act like natural infrared detectors, allowing them to sense the body heat of their prey, even in complete darkness. Infrared radiation makes up more than half of the sunlight that reaches Earth's surface. At sea level, the sun provides a total energy of just over 1 kilowatt per square meter. Out of this energy, about 53% is infrared radiation, 44% is visible light, and 3% is ultraviolet radiation. Microwaves are another type of electromagnetic radiation with wavelengths that range from 1 millimeter to 1 meter. In terms of frequency, microwaves fall between 300 megahertz and 300 gigahertz. This range is broad and includes different types of waves, such as ultra-high frequency, UHF, and extremely high frequency, EHF, sometimes called millimeter waves. Microwaves play a huge role in modern technology. They are used for satellite communication, radar systems, and even the simple act of heating food in a microwave oven. In engineering, microwaves are typically considered to start at 1 gigahertz, which has a wavelength of about 30 centimeters, and extend up to 100 gigahertz, which has a wavelength of about 3 millimeters. Radio waves have the longest wavelengths of all electromagnetic waves, stretching beyond infrared light. Like all electromagnetic waves, they travel at the speed of light. Naturally, radio waves are produced by events such as lightning strikes or energetic processes in outer space. However, humans have also learned to generate and control radio waves for various purposes. Radio waves are essential for communication technologies, including AM and FM radio, television broadcasts, radar systems, and wireless internet. Any wire carrying an alternating current can unintentionally emit radio waves, which is why electronic devices sometimes cause interference with radio signals. Different types of radio waves behave differently when traveling through Earth's atmosphere. Long radio waves can bend around the curvature of the Earth and provide consistent coverage over large areas. Shorter radio waves can reflect between the Earth and the ionosphere, allowing them to travel long distances. Very short wavelengths, however, do not bend or reflect much, so they require direct line-of-sight transmission. Very low frequency, VLF waves range from 30 Hz to 3000 Hz. The corresponding wavelengths are incredibly long, ranging from 100,000 meters, 100 kilometers, down to 10,000 meters, 10 kilometers. Due to the limited bandwidth in this range, VLF waves can only carry simple signals, such as those used in radio navigation. Extremely low frequency, ELF waves have even lower frequencies, ranging from 3 Hz to 30 Hz, with wavelengths extending from 10 million meters, 10,000 kilometers, to 1 million meters, 1,000 kilometers. These long waves can penetrate deep underground and even underwater, making them useful for communication with submarines. The military has built enormous ELF antennas, such as one in Michigan, to send slow but crucial messages to submarines that are otherwise unreachable. Thermal radiation is another name for infrared radiation that is naturally emitted by objects due to their temperature. Any object that is warm gives off infrared radiation, which is why we can feel the heat from a heater or a stove even if we are not touching it. The glowing red heat from an electric heater or a hot metal object is an example of this kind of radiation. Thermal radiation happens because the movement of charged particles inside atoms generates electromagnetic waves. Even relatively low-energy thermal radiation can have powerful effects. For instance, when it heats materials enough, it can cause ionization, which is the process of removing electrons from atoms. This is what happens in flames, where heat causes gases to glow and form plasma. It also plays a role in the browning of food, which is a complex chemical process that includes ionization at high temperatures. Blackbody radiation is a type of electromagnetic radiation that is emitted by objects with a uniform temperature. The intensity and color of this radiation depend entirely on the object's temperature. A blackbody is an idealized object that absorbs and emits the maximum possible amount of radiation at all wavelengths. For example, a black body at room temperature would appear completely black because it does not reflect any visible light and does not emit enough radiation for human eyes to detect. However, as the temperature increases, the object begins to glow. The glow of stars is a direct result of black body radiation. Stars have different colors depending on their temperatures. A relatively cool star, around 2,500 kelvins, glows red. Our Sun, which has a surface temperature of about 5,800 kelvins, appears yellow. Even hotter stars, at around 15,000 kelvins, shine with a bright blue-white color. The idea that light exists beyond the colors we can see was first discovered in the early 19th century. The famous astronomer William Herschel discovered infrared radiation in the year 1800. He used a prism to break sunlight into different colors and placed a thermometer just beyond the red part of the spectrum. To his surprise, the temperature was higher there, proving the existence of invisible infrared radiation. A year later, in 1801, the German scientist Johann Wilhelm Ritter made a similar discovery but on the other end of the spectrum. He noticed that certain invisible rays beyond violet light could darken a chemical compound called silver chloride, much faster than violet light could. This was the first evidence of ultraviolet radiation, which would later become crucial in photography and chemistry. The first radio waves were artificially generated in 1887 by the German scientist Heinrich Hertz. He built electrical circuits designed to produce oscillating currents, following the mathematical predictions of James Clerk Maxwell's equations. In 1895, Wilhelm Röntgen made another major breakthrough when he discovered X-rays. While experimenting with high-voltage electrical currents in an evacuated glass tube, he noticed that a nearby coated plate began to glow. Within a month, he realized that these mysterious rays could pass through soft tissues but not bones, leading to the development of X-ray imaging. 1 year later, in 1896, Henry Becquerel discovered that certain minerals emitted invisible rays that could penetrate black paper and expose photographic plates. His student, Marie Curie, later discovered that this effect was caused by certain elements naturally emitting energy, which she called radioactivity. Over time, scientists learned more about what these mysterious rays were made of. Henry Becquerel proved that beta rays were actually fast-moving electrons. In 1909, Rutherford and Thomas Royds showed that alpha rays were just helium atoms missing their electrons. A few years later, in 1914, Rutherford and Edward Andrade discovered that gamma rays were very similar to X-rays, except they had even shorter wavelengths, making them much more powerful. Beyond radiation coming from Earth, scientists also learned that radiation from space, what we now call cosmic rays, was constantly hitting our planet. In 1912, a scientist named Victor Hess proved their existence when he took an electrometer high into the atmosphere using a balloon. It took years to fully understand these cosmic rays, but this discovery changed how we view the universe. More breakthroughs came in 1932 when James Chadwick discovered the neutron, a particle with no electric charge. Soon after, scientists studying cosmic rays using cloud chambers discovered even more particles, such as positrons, muons, and pions. As technology advanced, even more types of radiation were created in particle accelerators during the second half of the 20th century.